Aaron will be the
So
backup.
So
Because-
Aaron, I'll give it to Aaron since he'll be the moderator, and then he can do the like he'll be helping manage. Or do you want me to give it to you once I'm done?
Moderator, yeah, you can give it to him.
Okay. Gotcha.
So where he should sit?
He's good right there.
Okay.
Yep.
Yeah. Because I want
he a
someone that
doctor?
do the, no,
Doctor
no,
Aaron, what's his last
not
name?
yet. Alan Poyer.
Poyer.
Poye.
Awesome. Well, I'll go ahead and start introducing.
You know, I make sure someone monitors the online chat. That's the question.
I'm gonna be on there.
Okay. You're gonna read the questions.
Yep, I'm gonna go ahead and start. We'll be good. I'll read out the questions for you, all right? All right, mic check. Can y'all hear me? Hey, good morning, everybody. I'm gonna go ahead and it looks like we're gonna be doing the parallel sessions right now. So we got 3 different sessions going on. This is the session for hurricane analysis and forecast system. So HAF. So welcome and thank you for being here. Just want to cover a little bit of a housekeeping item. So everybody knows if you were here yesterday, welcome back. If today's your first day, welcome. With that being said, I might cover some stuff that y'all heard yesterday. And if not, it might be some new stuff for you. So, thank you for being here. The first item, you want to go next slide? I am not Alikia. Since we're doing parallel session, she's actually in the middle. She is the main MC, but I'm just helping her out. But just a quick background on me is I did Air Force weather for 20 years, got my associate's degree in meteorology, then moved on to IT with my bachelor's, and then ended up getting my master's in cybersecurity. And I'm also the product owner for the ECE community engagement team. So pretty much seen everybody's names. Me, Jessica, and Jen really kind of worked on getting all this stuff organized. So again, we welcome you here and thank you. Really, so my role as MC here is going to be to kind of help facilitate things. So you'll see me in the background with the cards, kind of showing everybody cards to kind of help manage the time. Also, Aaron Poyer is probably going to be helping us out with that too. The one thing for anybody who's going to be a speaker today, I just ask, be mindful for the time that you have. It's really easy if everybody goes over a couple minutes that we end up running out of time really quickly. So pay attention. I'll have some cards out there to kind of give you a hint. If you do run out of time, it doesn't mean you have to stop immediately, but just be mindful and hopefully you can, bring it to a quick end. I'm not trying to be rude or anything. I'm just trying to make sure everybody has time to talk. Going to go ahead and go over the schedule overview. If it lets me. Yeah, can you advance? It's not working for me. There we go. All right, here we go. So for today, you're gonna see we're gonna be doing some of these community discussions, and then we'll also have oh yeah.
There we go.
There. Oh, yep. There we go. So we're gonna be doing our parallel sessions. At 10:30, 11, you'll see we'll have about a 30-minute break. After that, we'll be continuing with our parallel sessions, and then there'll be some time for Q&A. If you are on virtually right now, please log into Slido. I'll be monitoring the Slido, so you can ask questions there, and I'll make sure to give you a voice, and your questions should be answered. And at 12 o'clock, we will be having a lunch break. From 1-2, we're gonna also be having the community discussions, insights from industry and academia. So there's going to be some more parallel sessions going on after that. We'll be looking at a break, and then same thing, some more parallel sessions with the cross-cutting concepts. And then we'll be having another break, and then we'll also have a Q&A on that. So we'll be looking at finishing today at 5:30. If you have a chance, go ahead and look at the UFS-EPIC guide. It's going to have a lot more details on everything going on. So that should help you out on making decisions where you want to go. Again, if you were here yesterday, you kind of heard this. We will be live streaming, so a lot of the stuff being said and talked about can be heard. So just, I don't think anything crazy is going to happen. But just know. If you do decide to post anything on social media, please help get the word out. That's our hashtag right there. So anything to help get the word out will really help this program and help us out. If you want to get on Wi-Fi, that's going to be your Wi-Fi access point. Just make sure when you connect, you have to open up a web page and then hit connect again, and that'll allow you to connect. The internet's pretty quick and it's been working out for us. If you want to go ahead and access the event guide, there's a QR code. I'll leave this open for about 5 or 10 seconds. I see no phones. Anybody want to take a picture? Are we good? All right. And with that being said, I'm going to introduce our 2 session chairs, and then I'm going to hand it off to Aaron Poyer. Our first session chair, and I apologize, I'm going to say the name wrong, even though I was coached on how to say it. But CG1 Zhang, Dr. CG1 Zhang, and then also virtually we'll have Dr. Zhan Zhang. And then Aaron, if you want to take over for me, that'd be great, Aaron. We're both Aaron, so yeah, go. All right, now.
All right. Uh-oh, now I don't have anything. So oh, thank you. So thanks for joining us in this room and in the virtual room. I kind of jumped in to help since Zach is unable to be here in person. He's on remote. So just want to kick this off. And did you want to go through the bios here since you already rehearsed them?
Yeah.
So I will yield the floor to Shujin to do some bios on our speaker.
Our first speaker today is Zach Zhang. He's from EMC. He got his doctoral degree from FSU, and his talk today is operational implementation of NOAA's next generation hurricane prediction system, HAFS V1. Zach, the floor is yours.
Okay, can you hear me and see my slides?
Not yet.
Okay.
Hold tight a second, Zach. We
Yeah.
can hear you, but they're got to get your slides up.
Okay, I'm sharing
I think
screen.
the system is still pulling slides from the main room, so he just jumped out of the room real quick to try to get things situated. So hang tight for a sec.
Okay.
So we can have the discussion first before we talk.
Should I stop sharing? I see I'm sharing this.
Zach, just hold tight. They're gonna get it so we can see your slides. So you can just stay where you're at.
Okay.
And I guess we'd be remiss if we didn't do what everyone else has done and say, give yourselves a round of applause for all the awesome work that HFIP and others have done with HAVS since it's live and operational. And my shameless plug for the HFIP annual, November 14 to 17 in Miami. Be sure to join us. The information should be up on hfip.org early August.
Here we go. Yeah, Zach, it's yours.
Okay, you see my screen, right?
No, they flashed, then they.
I can just stop it and share it again. Let's see if it works.
Zach, it's not your
Yeah.
share that's the issue. It's at this end.
Okay.
Okay. So, Zach, go ahead.
Okay, you can see my screen, right?
No, yeah.
Okay, great. Okay. So good morning, everyone. Thanks for the opportunity. My name is Zach Zhang, and I'm the hurricane modeling team leader at EMC and co-leader with Xujing for the UFS R2O hurricane application project. Today, I'm going to give a brief overview of the operational implementation of HAFS version 1, which is the first UFS-based hurricane application in operations. So first, I would like to acknowledge all the contributors listed here. And so everybody knows that HAFS is a collaborative and community-based project, which involves many developers from different organizations and different expertise and many backgrounds. So without their contributions, we would not be able to achieve what we have achieved now. And I think that the list is still growing right now. As all of us know that 2 configurations of HAFS, HAFS A and HAFS B, of HEFS version 1 becomes operational on June 27th, 2023, just 1 month ago, and running along with the existing operational system HWF and HMA. So HEFS is running storms for all global oceanic basins, and HEFS-B is running TC tropical cyclones forecast for the NHC area of responsibility only. And HWF and HMA will continue running operationally in reduce the capacity and will be. You know, the HEFS is a brand new system and include many innovative features that are implemented in operational for the first time. And I will present HEFS version 1 configurations and some verifications from our 3-year retrospective runs experiment in the next few slides. So we have finalized the 2 configurations after testing and after testing various configurations and conducting numerous experiments. The color items listed indicated the difference between the 2 configurations. The domain coverage and the resolution are similar between the 2 configurations: 6 kilometers for the parents, 2 kilometers for the nests, and 81 vertical levels with 2 minima model top. And the vortex initialization threshold are slightly different between the 2 configurations. And also both configurations are 2-way coupled with HiCom ocean models. But HEFS-A is also 1-way coupled with WaveWatch 3 wave models. So I will elaborate some of the details of 2 model physics suites in the next slides. So this table lists all the physics schemes used in HEFS version 1. Suite 1 is used in HEFS-A configurations, and Suite 2 is used in HEFS-B configurations. The color item indicates the difference between the 2 physics suites. You can see basically the major difference is the microphysics schemes. HEFS-A uses GFDR microphysics and HEFS-B uses Thomson microphysics. And also there's differences between the PBR schemes and convection schemes between the 2. The tuning methods are slightly different. So the input, I'm going to talk about the upstream dependency of HEFS models. So GFS model and RTOF are the upstream and host model for HWF, for HEFS, and which are used to generate atmospheric and oceanic initial conditions and the lateral boundary conditions. And HEFS DA system relies on GDAS ensembles, and also of course the observation input data. The ENKF, as you can see in the flowchart, ENKF system is not included or is not part of the HEFS version 1, but the configuration is available, which I will talk about later in the later in my talk. So to ensure the HEFS version 1 produces improved and robust results, we conducted 3-year retrospective runs for both North Atlantic and East Pacific basins from 2020 to 2022. So this slide is showing the earlier model verification results for North Atlantic and at left and East Pacific at the right column. So the two top configurations are the track and intensity forecast. And the 2 bottom is the same thing, but in the scale space. In the scale space, as you can see that both North Atlantic basins, both HEFS configurations are improved. and both schemes are improved, and also in the about 10% improvement compared to the HWolf, and also the intensity forecast improvement skills are close to 10% for leading times beyond the day 2 for HEFS-A for HEFS-B, and about 5% maximum for HEFS-A. Oh, I forgot to mention that for EPIC, the track forecast skills are positive for all lead forecast lead time about 10%, 5 to 10% improvement. The intensity forecast skills are neutral to and turn on the positive at day 1, and about 10% for more skillful than HWolf at day 5 for both HEFS configurations. The only exception is on day 1 for HEFS-A, which is kind of behind, the forecast skills are behind HWolf. So for JTWC basins, HEFS did a very good job in terms of track forecast for both West Pacific and the Southern Hemisphere storms, about like a 5 to 10% track forecast improvement for West Pacific, and also 10 to 20% track improvement for Southern Hemisphere. And
sorry, just want to give you a heads up. You have 5 minutes.
Okay, sure. Okay, so I have 15 minutes, right? What I'm showing here, I only
you have 5 minutes remaining.
Okay, right. Okay, so okay, HEFS has a neutral impact on the intensity forecast at earlier time and improvement at later lead time for both West Pacific and Southern Hemisphere. Just for the sake of completions, I also listed North Atlantic Basin verifications, but the sample size, as you can see, are small, so it's difficult to draw any conclusions for the North Indian Oceans. So we also compare the pressure wind relationships between HEFS and HWolf. What you can see here is that for North Atlantic basins, HEFS produce a very similar pressure relationship compared to HWolf, but at East Pacific, you can see the improvement. The wind's pressure relationship are significantly improved compared to HWolf, especially for the stronger storm. So the rapid intensifications verifications, you can see that it's very important. It's another metrics we are looking at. So we calculated the rapid intensification RI performance diagrams for storms at NHC basins combined and the JTWC basins combined. In general, the HEFS RI performance are very similar compared to HWolf and HMI, what you can see here. So this is the scoreboard or score tables that already that was shown by Dr. Morgan yesterday. It's the same slides. Basically, it summarizes all the verifications we did from HEFS 3-year recharge spectrum's performance compared to HWolf. The green box indicates the improvement of HEFS over HWolf, and the blue box indicates somewhat the HEFS has a neutral impact and compared to HWolf. Of course, the orange box indicates that there is some room. So HEFS is for improvement. HEFS is still behind HWolf a little bit. I mean, the major issue is RI performance. In general, you can see the green box actually dominates the tables. So two configurations, I already talked about two operational configurations. These are only the 2 snapshots of our instances. There are many configurations options available for research to be explored. I listed some of the options here for your reference. And for domain configurations, you can see you can choose global nest domains or regional nest domains. Also, in further, you can choose For regional domains, you can further choose storm-centric and basin-centric domains. For DA system, you have choice to conduct the DA for both parents and nests, and also or you can do DA for nest only, which is the operational configurations. And also there are many model physics schemes for you to choose from. And we have you can choose between the two. There's two ocean models to couple with. You can choose either to couple halves with HICOM and also the MOM6. So this is my last slide to summarize. I'm not going to go through all the items listed here, but just would like to emphasize that the 4 credits should go to the entire EMC hurricane modeling teams and NHC teams, AOML, and the DTC teams, and all our research and operational collaborators for a successful HAFS version 1 operational implementations. I guess I will stop here to take any questions. Thank you.
Yeah, we have about 1 minute question. Anyone? Online question? Okay. If no question, let's move on to the next talk. Next talk from NHC, Dr. John Martinez. He is he's representing NHC and CERA. He got his PhD degree from CSU, right? Yeah. Dr. Martinez, go ahead.
Sorry, John. I just want to jump in real quick. I know that some of the graphics that Zach had up were a little hard to read here in the room. If you go to the live stream that's available from the schedule, they are a lot clearer than the projector can handle on some of the fine lines. So just as reference for folks in the room that might be having a hard time reading some of those.
Yeah, go ahead.
Is the clicker working now, or do I gotta slide it?
Should I don't know, this one is working now.
I'm trying.
Go ahead, try.
Yeah.
Once I get it out.
Hold on 1 second.
Yep.
For those online, we're having an issue moving the screen share back to the room. So bear with us for a moment.
Yeah, I have some material that I could work there. Huh? Cool. Are we good there?
Yeah, we're good. Go ahead.
Yeah, I don't think I can advance it with the clicker, so I might have to have somebody advance.
Can you try it?
Yep, I'm trying. Oh, there we go.
Oh yeah.
Perfect. Everything set?
Yep.
Awesome. Well, good morning, everyone. It's great to be back in Boulder and seeing so many faces from Miami here. I'm sure everyone's enjoying the slightly drier weather, although same high temperatures. Yeah, I hope that the length of my talk here, the title doesn't actually foreshadow the length of the talk, because that would be a problem. But I'm really just going to walk through an overview of the model evaluation process at the National Hurricane Center. And I'm going to be doing this through the lens of the HAVS version 1 models that were just recently implemented in operations. So let's start from the top here. You wake up one morning and you're told that the HAVS V1 retrospectives are going to be on your desk. So what do you do aside from panicking? First and foremost, we were planning and coordinating with the forecasters and the hurricane specialist unit. So the document on the left there is intentionally shown with small font. So this was something that we devised, a list of experiments that we wanted to test. Again, this was with the forecasters and the NHC directorate. So just gives you a sense of the comprehensive nature of the evaluation that we were doing. A lot of communications with the Environmental Modeling Center. So special thanks to Zach for fielding a bunch of requests that I had, along with a bunch of forecaster requests. And then the third bullet there is probably understated. Throughout the whole process, I am adaptively integrating feedback from the forecasters, working together with various folks at the technology and science branch and trying to pull this together. So we had a Google Drive directory at some point with, I don't know how many presentation decks in there showing some results. And of course, briefings with EMC. So here are what I believe to be the 5 key elements for the model evaluation process. I just put these together based on what I did for the HAVS model evaluation. And I'm going to be talking about these here today. So we usually begin by generating a fresh set of the early guidance forecasts. And that's the first step in the process, determining the optimal interpolator offsets. Then we work on testing the addition of the replacement of models and the consensus aids. And this is especially important because these consensus aids provide some of the most valuable information to the forecasters and some of the best guidance as well. So the third one is a pretty big project in and of itself, adding or replacing models in HICA. That is the HFIP corrected consensus approach that provides track and intensity forecasts. And it's among the best guidance available to the forecasters. And then we're going to assess, for example, the performance of the individual models, in this case, HAVS relative to HWRF and HMON, and then, of course, synthesizing those findings and producing a recommendation for the forecasters, and then having the forecasters and the directorate coordinate to provide a recommendation for EMC. So I'm going to focus a little bit on the consensus aids. As I mentioned earlier, these provide some of the best guidance to the forecasters. So there are many consensus aids available. This list is not exhaustive, but these are some of the more important ones that we tested out. We have, for example, the track variable consensus and intensity variable consensus. These are simple, equally weighted consensus models at the National Hurricane Center. And then we had to replace HWRF and HMON with the HAVS models to test the performance there. Equivalently, we have the wind radii consensus model, HICA, and then there are some probabilistic aids that I didn't evaluate myself, but others worked on at the National Hurricane Center. So we're not going to talk about those here today. This is just to give you a sense of the overall process. So the foundation for doing these evaluations really comes from the forecast verification software that's available at the National Hurricane Center. This was developed over many years by James Franklin and several folks at the National Hurricane Center. I got a screenshot on the left there just to give you a sense of how this software is highly configurable. So it's written in Fortran. I've put together several Python post-processing scripts with Ben Trabing. And you have options, for example, to look at verifications done with the rapid intensification metrics from HFIP. You could condition based on the presence of watches and warnings, aircraft reconnaissance, distance to land. There are many things in that list that you can add to the verification. And some of the cool features are that you can look at single storms, multiple storms over a season, multiple years. You can even do multiple basins if you'd like. You have access to all of the forecast errors, so you can easily compare some of the error statistics. And then a particularly useful feature for the work that I did was your ability to generate the consensus aids on the fly. So all of those consensus aids that I mentioned earlier, the track and intensity, you can plug and play with whatever models you'd like and quickly develop a verification for those. And then just worth noting here that Clipper, the climatology and persistence, and then the decay Chi-4, so that's the statistical hurricane intensity forecast for the climatology and persistence that is used in the annual reports for the baseline. That's also available in the forecast software, or sorry, the forecast verification software. So we're going to be using this tool to talk about some of the results here in the model evaluation process. So starting with that first step, generating a fresh set of early guidance forecasts. This is really prerequisite to all of these subsequent analyses. And we're doing this because we want to test the individual models in the consensus aids. So to give you a sense, I'm sure many of you are already familiar with this process, but to give you a sense of why we need to do this, the dynamical models usually take a little while to run, and they arrive quote unquote late to the forecasters. So let's say you have the 12Z synoptic cycle with a forecast issued at 15Z. The model is usually not going to be available by 15Z. So the figure on the bottom left there in what was supposed to be blue, but and maybe it's a little bit difficult to see there. The one that starts at the very bottom in the lower left corner, that is the late model forecast from 6Z adjusted backwards 6 hours. And so at 0Z now for the 12Z forecast, you could see that the forecast intensity is a little bit low compared to that black dot. That black dot there is the CAR Q entry for 12Z. So the interpolation process entails taking the late forecast, interpolating it to 3-hour time steps. Then we smooth it 10 times. And we're going to adjust that to the adjust the intensity at t equals 0 to the CAR Q entry. So the line that begins on that black dot that looks relatively smooth, that's the early guidance forecast after those steps were taken. And so the last step is to relax the intensity offset that you apply at t equals 0. And to do that, you need what's called these offset start and stop times. And that's really the crux of determining the interpolator offsets. So this slide is a little verbose, but I just wanted to quickly walk through here how we determine those interpolator offsets. I developed several baseline definitions for comparing some of these results. For example, if you just offset by a constant factor, you could just simply lag the forecast. So you could take that 6-hour forecast and shift it the way that I did in that first step. You could apply the offset only within certain time windows. So there are many ways you could define these baselines. And then so for each one of those baselines, we're looking at the right here now, we're calling those M baselines. And for each sort of start and stop couplet, we can just sum the skill scores over that 120-hour forecast. So and determine what's the best set of interpolator offsets that way. So here's an example just for the HAFS-A model, and this is the North Atlantic Basin. The top left is the constant, top right is the lagged offset, bottom left is the offset at only 6 hours and prior, and then offset at 12 hours and prior in the bottom right. And these are showing the skill relative to those various baselines listed there. So without going into too much detail, there are many lines on this plot, and it's impossible to tease out what's going on here. And I just boxed in what ultimately ended up becoming the operational interpolator offsets for HAFS-A. And so that was 0 and 48 hours. So if you just look at each of those baseline plots, again, there's a lot of lines, but the one that has the highest skill score pretty much among all of them is the one that we ended up picking. So we're really trying to choose the interpolator offsets that give us the best intensity forecast. So quickly walking through some of the results from the consensus aids, because this was a key element in the process that I mentioned earlier. We have the track variable consensus. This is a variable consensus, meaning that there's not a fixed number of models that are required to form the consensus. You just need a minimum of 2 members, and they get an equal weight. So this is just a simple average. And for the example that I'm giving here, I'm only looking at the North Atlantic Basin, and we're looking at replacing, in this case, HWRF with either HAFS-A or HAFS-B. In operations, I should note that right now we have all 4 of the models, but the test that I'm showing here, we're just going to replace HWRF with HAFS-A. And so these are the types of verification measures that we're generating with the forecast verification software. And these are some of the results, for example, that we use to inform the decision ultimately, or maybe I should say the recommendation from the National Hurricane Center from this model evaluation process. And so we have the mean absolute error on the top left, a long track bias on the top right. We have the skill relative to a baseline. In this case, it's TVCN with HWRF. And then the bottom right, we have the cross-track bias. So a little tricky to tease out the colors on the screen there, but overall, the TVCN with halves A was performing a lot better compared to HWRF. We're seeing on the order of 2 to 3% improvement in the track forecast at most of the lead times there. And then we saw a reduction in the long and cross-track biases. So this was great news. Results were pretty much mirrored in the EASPAC, which I'm not showing here. Jumping to the intensity variable consensus, again, this is a simple consensus model, and we're replacing HWRF and HMON with the two halves models. Again, worth noting that in operations this season, since all those models are being run in parallel, we have all 4 of them in the consensus, so even better performance than what you might see here. Pretty much the same results, or sorry, I should say the same layout, except in the bottom right, we now have the frequency of superior performance for the intensity consensus aids. And so overall, IVCN was performing better, especially in the first 2 days with the addition of the halves models. And then we saw a slight reduction of the skill in days, I think that's around 2 to 3, maybe days 2 to 4 there before it sort of flat, sort of evens out between the two models. But great news, a reduction of the intensity bias for IVCN with the halves models. And then if you look at the frequency of superior performance, they're really on par with one another, despite, you know, what might betray you in terms of the reduction in skill at days 2 to 4 there. You're getting a performance that's roughly 50-50, you know, the IVCN with the halves models performing just about as good as with HWRF and HMON. So I'm going to quickly step through. Actually, I'm going to skip the wind radii consensus models. Maybe it's worth noting here that if you just eyeball these plots here with all the different wind radii metrics that we have, the halves models were slightly increasing the small bias in RVCN, and we got a minor reduction in the skill as well. But this is only for the North Atlantic. In the EASPAC, it was pretty much a grand slam across the board for the wind radii consensus model. So jumping into the results for HICA, this is a lot more involved of a process during the model evaluation. So we have to recreate the training data set, and then we have to run some experiments with the new models. And so HICA is a variable consensus model. Again, it doesn't require a fixed set of models to produce a forecast, but these models are given unequal weights. And so it's worth noting that the forecasts are developed, or I should say the training data set is available, you know, for all of the models that are in there. But then what goes into HICA is developed the forecasts are developed on the fly based on what models are available, meaning that, you know, if HWRF is not available, then it just doesn't go into the forecast for HICA, and the weights are adjusted on the fly accordingly. So for the training, we have to leave one storm out. We're essentially creating a forecast for every storm except the one that's being forecast. And I'm just going to show a quick example for track and intensity here based on the addition of halves A and halves B. So, okay, here we go. And actually, I should say that these results include HWRF and HMON too, just to give you a sense of how great of an improvement we get with all 4 models. The operational configuration is a little bit different now, but you could see that we get somewhere on the order of, you know, 5 to 10% improvement in the track skill with all 4 of those models in there. That's HWRF, HMON, and the 2 halves models. And then for the intensity, we're similarly getting an improvement, you know, on the order of 5 to 10% at many forecast lead times. So it would be great to have all 4 models, but obviously that's not feasible computationally and just in terms of management of the 4. So halves is going to be replacing these officially next year, and we're going to have to reassess. Running out of time here. These are the rapid intensification results. Zach talked about them a little bit, pretty much comparable performance across the board for the 4 models there. So I'm not going to go into details on these results. Jumping into the summary, I hope you got a sense of how this process of doing model evaluations at the National Hurricane Center is multifaceted. It's also multi-organizational. We were coordinating with several folks from CIRA, going to briefings with EMC, with HRD, DTC, several others, a lot of acronyms there for you. Moving forward, I think on the National Hurricane Center side, we really want to standardize this process and make it a lot easier and more efficient. So I have some screenshots at the bottom there for developing standard operating procedures to do this, and that way we can optimize the model valuation process in the future. And then looking ahead, we really want to do parallel evaluations with MET+, and then it would be great to transition into a community-based tool for doing these evaluations at the National Hurricane Center, so that way we have a homogeneous comparison when we're doing these coordinations. So I have a screenshot on the right there just showing, for example, we have the NHC forecast verification software on GitLab now. It's not publicly accessible at this point, but I've been making a lot of changes to it, and I'm hoping that this sort of streamlines the process of doing parallel evaluations with MET+. So I'll stop here, and sorry if I went a couple minutes over there.
Back to you in the room. Any question in the room? Yes. Oh, Mike.
Wait, then. Is it okay? Thanks for that talk. I actually just wanted to ask a question about the MET+ evaluations. So in the DTC, we are working on putting MET+ into the HAFS workflow this coming year. And so back in, I think, 2014, when we originally made the MET+ software, we worked with James Franklin on getting the capabilities to line up between the NHC verification software and the MET-TC. And so I just wanted to mention, if you have like configuration files and settings that we can go back and just make sure that everything's lining up, I think we can work together to make sure that we're getting, the same verification results, hopefully going forward. So I just wanted to make that point.
Yeah, thanks. That sounds great. I think we could definitely coordinate to double check on all of the features that are in there and whether or not they've evolved over the past few years. And I think maybe even adding some of the features if they're not already in MET+. I'm not familiar. So for example, like generating the consensus A's on the fly, like that's a really helpful tool. So that might be available in MET+ as well. But yeah, sure. We should definitely coordinate. Thank you.
Just want to mention real quick that since we are short on time because of our technical issues, that there is a Q&A session in the portion after the break, I believe. So if we do end up having to hold questions, you can ask them at that time as well.
Yeah. Online question, any? Okay, let's move on. Next speaker from Princeton University and GFDL, Kun Gao. He graduates from University of Rhode Island. Kun, go ahead.
Okay. Now before I move forward, can I get some confirmation that you can see my slides and also hear me okay?
Yes, you're good.
Yeah.
All right, sounds good. Thank you. Now, I really appreciate the opportunity to give this presentation virtually. Next, I'll share some science we learned from a recent high-resolution hurricane model development effort at GFDL. This talk is mainly based on our recent JRL paper listed here. First, I'd like to introduce the model we have been working on for hurricane prediction. The model is called T-Shield, and it's one of the configurations of the GFDL unified all-purpose, multi-purpose weather prediction model shield. We use a two-way nested grid in T-Shield. We have a large static nest covering North Atlantic. Resolution in the nested region is about 3 kilometers. A T-Shield actually had served, had served as the precursor of the HAFS system. And similar to HAFS, T-Shield is also built on the FA3 dipole and GFS physics. And because of the similarity between the two, all the advancement we made in T-Shield can be easily integrated into HAFS. And we did have a few successful stories in this regard. Also, we use T-Shield for experimental forecast, real-time forecast during the active hurricane season, product, and also the information related to the model configuration can be found on our shared website. Now, before I move on to the scientific stuff, I'd like to quickly highlight the performance of the real-time T-Shield in the last hurricane season. This model excelled in terms of track prediction. On the left, I'm showing the forecast of Hurricane Ian's track at 2 different initialization time in comparison with a few other operational models. Black is observed track, and T-shield is red. You see that T-shield captured the correct landfall location at least a day earlier than other models. And the predicted track, predicted landfall location also had been pretty consistent. The mean track error in T-shield over the entire season is also pretty impressive. This doesn't really happen by chance. Good performance of T-shield here actually benefited from many years of development. We also learn new scientific insight from this process. And that's something I want to share next. A little background is that the impact of convection on hurricane prediction is well known to the modelers, but usually the underlying mechanisms are not well understood. And this is partially because there's usually complex multi-scale interaction involved. And here we want to offer an example showing that, showing that the hurricane track prediction in high resolution model is significantly affected by the result convection. And those convective activity may not even associate with hurricanes at all. We also offer physical explanation for such sensitivity. Now the story starts with a subtle change in the horizontal advection scheme. During T-shield development, we tried two horizontal advection schemes in FA3. Both are suitable for high resolution applications. For convenience, I'll call them HRD5 and HRD6 respectively. HRD5 is a virtually invisible scheme, and it's the least diffusive option in FA3. HRD6 is slightly more diffusive. To give you a direct sense on the implicit diffusivity related to the two schemes, here I'm showing results from one-dimensional advection test initialized with a rectangular wave signal. Solid dotted lines are the same signal, but after a few advective cycles. You see that the HRD5 scheme produced more small-scale features, and the same signal in with HRD6 is relatively smoother. Now, overall, both schemes are not very diffusive, but turned out that the TC track prediction in T-shield is very sensitive to the choice of the scheme here. So now let's look at some actual forecast. Here I'm showing the predicted tracks of Hurricane Dorian at different initialization time. And this is the set with HRD5 scheme. You see that there's some spread between earlier and the later forecast. And earlier forecasts tend to drift to the east of the observed track. In comparison, this figure now shows the prediction from a different configuration. Everything is the same, except that we change the horizontal advection scheme to HRD6. You see that we have a more consistent track prediction now, and the eastward track bias in the early forecast is much reduced. If we look at other storms like Hurricane Laura, we see similar sensitivity. HRD6 gives a much consistent and better track prediction. And to make sure this is a robust improvement, we did many retrospective forecasts spanning 5 hurricane seasons. And here we are looking at the mean track error from the 2 T-shield configurations and also 2 operational models here as reference. If we focus on the comparison between the 2 T-shield configurations, the blue and also the green lines, you see that the mean track error in the HRD6 set is reduced by nearly 10% at day 4 and day 5 compared to the HRD5 run. And the difference is actually significant at 99% level. And the mean error reduction here is actually directly related to a reduction of the mean eastward track bias. And we also see this from the selected track prediction earlier. Now, why this is happening? So next, let's look at the large-scale flow to get more insight. Here we are looking at the mean 700 millibar gel potential height field. The left two figures are the time mean of all the forecasts we made. And the rightmost figure is the difference between the two. You see that the most significant difference between the two T-shield configuration lie in the western edge of the North Atlantic subtropical high. On average, the high pressure system extends further westward in the HRD6 set. And the weakened subtropical high in HRD5 rounds makes the westward propagating storms recurve to the north earlier, therefore resulting in a significant eastward track bias. But in the HRD6 round, this bias is much reduced. Now, one essential question remains, and that is, how are all these related to the change of the horizontal advection scheme? And this leads us to make the following hypothesis. That is, the change of the horizontal advection scheme affect the behavior of the model result convection in terms of their occurrence and also the spatial distribution, which in turn could have upscale impact on the subtropical ridge. And if this is true, then the sensitivity to HRD should also depend on the model's ability to resolve convection, or equivalently, the model's horizontal resolution. So next, to facilitate further analysis, I'd like to focus on a single case. And ideally, we should exclude the TC in this single case. So we don't need to worry about the complicated interaction between TCs and the large-scale flow. The question is, can we reproduce same difference pattern here in TC-free forecast? Answer is yes. This lower panel—
You have 5 minutes remaining.
Okay, thank you. Yeah, lower panel is from one single 5-day forecast, and there's no hurricanes or tropical storms at all during the 5-day period. We see that even in this single TC-free case, there are similar large-scale difference pattern as in the multi-case mean. And this is really great news. And next, I'll focus exclusively on analyzing the results from this single case to get more physical insight. Next question we want to address is that, does the sensitivity to horizontal advection scheme depend on resolution? Answer is also yes. If we double the grid spacing in the nested region to 6.5 kilometer, we see the difference between the two rounds becomes much weaker. And if we further increase the grid spacing to 13 kilometer, then the two experiments produced almost identical results. And this provides indication that the large-scale circulation sensitivity to the horizontal advection scheme is tied to the model's ability to resolve the fine-scale convective features. And in the next slide, we'll try to get a direct sense on how the fine-scale features change with HRD at 3 kilometer resolution. Now we begin with a visual check. Here we are looking at the snapshot of the vertical velocity field at 500 millibar. And you clearly see that there's more active convective features in the HRD5 round. Excuse me, Xu.
2 minutes left.
Oh, sorry. Okay, thank you. And I should be able to finish in time. A zoom-in view on the right clearly shows the difference. You see that the result convection with HRD6 is smoother and also more organized. And here I'm showing the variance spectral of vertical velocity field in the two experiments. And this is to quantify the distribution of the vertical motions across different spatial scale. And we see that the two configurations mostly differ at a small horizontal scale and roughly below 4 times of the grid spacing. And there's a reduction of the small scale motion in the HRD6 round compared to the HRD5 round in this regime. And then we can further quantify the spatial distribution of the result convection. Here I define a quantity called updraft density, which basically describes the occurrence of the intense updraft at 1 by 1 degree boxes. Important message is that there are more updraft occurring in the western edge of the subtropical ridge in the HRD5 experiment, and which indicates the more active result convection have occurred and eroded the ridge significantly in this region. And we don't have this issue in the HRD6 run. So now a quick summary. So key message is that we found that a better regulation of the fine scale convecting feature lead to improved track prediction in GFDL T-shield. And I also want to emphasize that this work has important implications for the hurricane resolution model, high resolution hurricane model. We provide an example showing that the use of high resolution doesn't automatically make things better. We do need to pay a lot of attention to the behavior of the marginally resolved features and also their upscale impact. That's all I have. Thank you.
Thank you. Yeah, we have more seat here if you want to see. Any question in the audience? Question online? I think we leave all the questions to the Q&A session after the whole session complete. The next, let's move on. In interest of the time, let's move on. Our speakers stay so that we can after that 11:35 we will have the Q&A session.
Real
So
quick, we did have some questions online, but let's wait for the Q&A session because we're running kind of late right now.
Yeah.
So I'll definitely get those out there.
Okay. Yeah. Save that question and I give you time to ask. Next speaker, Catherine Newman. Catherine Newman, she represents NCAR DTC, and she is a task lead in this effort. Catherine.
All right, thanks and good morning, everyone. I'm Catherine Newman, and I'm going to be discussing an evaluation. Oops, did this advance? Oh, yep, an evaluation of QPF for the HAFS model, and I want to acknowledge my co-authors. And this work was done under the DTC. Can this advance or am I pressing here? Oh, there we go. Sorry. All right, so a quick overview. So QPF verification provides insight on both model storm structure and total precipitation, which is useful for understanding model processes. So we can look at microphysics, PBL, other parameterizations, as well as interactions between the parameterizations. And establishing tools for large sample evaluations for QPF enables regular assessments of QPF. So this work is to provide an assessment of the recently operational UFS-based hurricane analysis and forecast system for TC precipitation forecasts. This work focused on a storm-focused evaluation using a variety of different methods, and we're looking at the performance over both land and water. And as has been mentioned quite a bit so far, the HAFS VU1 went operational just last month, and so the two configurations of HAFS will be replacing the HWRF and the HMON. All right, so for the two configurations of HAFS, HAFS A and HAFS B, they were evaluated for all North Atlantic Basin storms in the 21 and 22 seasons. So this was a little under 40 storms total in this sample. We did the evaluation on the parent domain, which is 6 kilometers, so the convective parameterization was on. But we masked the region to focus on the storm region for this evaluation. And then we also ran the verification over HWRF in order to provide an operational baseline. So looking at the table, we can see the different physics parameterizations that are used in the different configurations or models. And I wanted to highlight the microphysics to point out that each of these different configurations has a distinctly different microphysics parameterization used. So for the methodology, we use the advanced or enhanced model evaluation tools, or MET+. And so if you are familiar with MET+, I listed the different tools that are in our workflow. This is 6-hour precipitation accumulations, and we employed a track shifting logic that looked at the model track and the best track and shifted the field to account for those differences. We had land and water designation in order to use different observations for land versus water. And then we used some storm masking in order to focus on the storm region. So this was a 600 kilometer mask around the best track at each valid time. So for each valid time, as we did the verification, we used the specific mask for that storm. And that was based on the best track. And then for observations, we used the iMERG over water, which is the integrated multi-satellite retrievals for GPM. And then over land, we used the climatology calibrated precipitation analysis, or CCPA. And all models and observations were regridded to a common grid. So looking at some statistics here, this is looking at equitable threat score. So if you, just a reminder, ETS 0 would mean no skill, 1 would be a perfect forecast. On the left-hand side, I'm showing greater than or equal to 0.1 inch threshold, and on the right side is greater than or equal to 2.5 inch threshold. The blue lines are for halves A, the green lines are halves B, and the purple are HWRF. And the solid lines are the straight model output post-processed, and the dotted lines are the shifted tracks, just to give you a feel for that. And so we can see that the impact of shifting is less where there's more grid cells with precipitation, so at the lower thresholds. But we can also see that shifting helps stabilize the skill scores at longer lead time. So if you look over at the larger threshold, you can see where the dotted lines really stabilize out, whereas at the longer lead times out to about 5 days, the non-shifted tracks, the score drops down. And so one thing I wanted to mention is that the skill scores are a bit low here. We did find in the literature that there are issues with ETS calculations for random chance adjustment when you have many rainy grid cells over a small domain. So as we're looking at a smaller subset, and so that might be impacting the lower ETS. When we did the full DO1, we had much higher, well, a little bit higher ETS. That could be that the area with the TC is a little bit more, has a little bit less skill, or it could be this issue. So I just wanted to mention that. Looking at frequency bias, again, F bias, 1 is a good forecast, greater than 1 is over forecasted, and less than 1 would be not forecasted frequently enough. The plots are the same as the previous slide. We see that we over forecast precipitation for lower thresholds and under forecast precipitation for larger thresholds. And we did see that the shifting doesn't really impact the results, which isn't too surprising given that we're looking at F bias. But I did want to note that in the lower thresholds for HWRF, we do see a difference. And this might just be due to some larger track errors that are impacting the mask that we used. So going forward, I'm just showing the shifted tracks since we saw that it either improves or doesn't impact the results for the most part. So this is looking at ETS over land. The left-hand panel in blue is halves A, the middle in green is halves B, and then the right side is HWRF in purple. And we're looking at different thresholds from 0.1 inch up to 5 inches, with the lighter colors being the lower thresholds, and then it gets darker as you go to a higher threshold. And so here we can see that the larger thresholds and the lowest have the lowest skill. That lowest threshold might be that reason that I was just mentioning on the previous slide. Whereas the intermediate half inch to 1.5 inch performs better for the halves configurations. But we do see that the HWRF skill is a bit more stable with lead time. You don't have that drop as you get out to 5 days. Looking over water, so this is against iMERG, same setup. Here we can see that the greater than or equal to 0.1 inch threshold has the lowest skill, again, likely that same reason. But then we also see that the track shifting is fairly consistent throughout, that results in fairly consistent skill throughout the forecast. Looking at F bias over land, same setup here. The larger thresholds perform fairly well as they're near 1. The smaller thresholds tend to over forecast precipitation for all models and configurations. And then over water against iMERG, the larger thresholds tend to under forecast precipitation for all models and configurations, and the smaller thresholds tend to over forecast precipitation for all models and configurations. So quickly looking at a case study of Hurricane Ian. So this is looking at all the 12-hour forecasts. Here we have the grids in cylindrical coordinates and then normalized by RMW. The shading is precipitation accumulation in millimeters per 6 hours. And going left to right, we have iMERG, halves A, halves B, and HWRF. And this is composites from September 25th at 0Z through September 28th at 18Z, which is the time period when Ian was in the Gulf and making landfall in Florida. And here we can see that iMERG shows a larger storm with more precipitation in the eastern semicircle. The halves configurations are fairly similar, so the two center panels. The HWRF has more compact and more intense precipitation near the center. And there's less precipitation in the eastern semicircle for HWRF. And then finally, we can see that there's this persistent outer band in the upper right quadrant around 5 to 10 RMW in the iMerge. And you can also see that that is the case and has fairly good placement for the halves configurations. The same data, but showing it here in distributions, we have, so this is against iMerge and the charcoal. And so these are showing bins of 0.4 RMW, again, 12-hour forecasts, histograms by RMW. You can see the halves gradients, so the first two panels, left to right, are moving from the center, better match the iMerge observations, whereas HRF has these higher intensities closer to the RMW and then a steep drop off around 2 to 3 RMW. And then finally, looking at these results using modes, this is the method for object-based evaluation, where mode is an object identification algorithm that basically mimics a subjective human forecaster's ability to match objects and observed and forecasted objects. So this is just showing one example. This is HAFS-A on the left, and then the observation for iMerge on the right, 6-hour accumulations for a specific initialization. And you can see where the storms are located. And the right panel is showing what mode identified for the objects. So the red observations, the red is the observations and the blue is the model. And so you can see where, those have been identified. And so using this information, this is for all of the grid points with precipitation within all of the objects for Hurricane Ian. This is looking at a PDF of log frequency versus 6-hour precipitation accumulation. And for HAFS-A and HAFS-B, we can see that there's more light precipitation and it's lower throughout most of the distribution. Whereas HRF, we see less light precipitation with more heavy precipitation, likely due to that over forecasting near the core that we saw with the RMW analysis. So everything is lining up as far as what we're seeing for results. So to conclude, what we're seeing across all the different evaluations is that the more complex microphysics and the HAFS configurations better represent the TC precipitation and the features of the TC. The HAFS-V1 configurations tend to over forecast precipitation for smaller thresholds and under forecast precipitation for the larger thresholds. And considerations are needed for assessing skill for the lowest thresholds for the smaller verification domain and the higher number of precipitating grid cells. And so we're looking at other verification like FSS, some neighborhood methods. And I just wanted to finish up by mentioning that the HAFS-A and HAFS-B retrospective runs were conducted by NOAA EMC and HRD hurricane teams. And so we really appreciate getting access to that large data set. All right, so thank you.
Thank you. Keep the time.
All right. Yep.
Question in the room?
I think Michelle has one.
Yeah, thanks, Catherine. Very, very interesting talk. And there is general interest in finding out, how HAFS is going to perform for this season and in the future for, land-based QPFs and conditions during landfall. So in that context, I was wondering, are there measures to also look at cumulative precipitations, 24-hour or an event-based accumulation?
Yeah, so this is 6-hour accumulation, but we can certainly do 3 and 24 other accumulations. The reason why I selected 6 here was just because we're doing the track shifting. So then we had the 6-hour for the different track. But yeah, we could certainly do other accumulations. Yep.
It'd be interesting to look at it.
Okay. Yeah. Thanks.
Any further question? Online? One question? No? Okay.
All right. Thank you.
Okay. You stay here. If you have more questions, you think about that, then come. Okay. Next speaker from LML, Hensuk King. She's our ocean modeling expert. She graduated from UI, University of Rhode Island. Thank you.
Thank you. Okay, so this is project. Oops, did I do that? Okay. Working toward the version of HAPS systems. It's too soon to working on it, but so we took a first step by coupling MUM6 in place of a HICOM, and then I'm going to show some preliminary results. And then we're going to run this one as a real-time demonstration for this season. In fact, next month, starting next month. Okay, perhaps this slide shows that UFS components in the blue boxes and then a square box representing either boundary conditions and the data simulation for atmospheric side. And one thing you notice that it's a blue box MUM6 is sitting in place of HICOM. And while we are coupling with the MUM6, we need the CDAPS and the datum on the right side, which covers that the area exclusively excluded by each domains. So I'm going to talk about this one later on. Okay, so first model configuration. There are two operational configurations, HAPS-A and HAPS-B, but currently we coupled MUM6 in HAPS-A. And then third point is that we have not tuned the parameters yet. So this is just simply replacing HICOM with MUM6. And then initial and boundary conditions for MUM6 is exactly same as HICOM in the currently HAPS-A and then HAPS-B. And the preliminary results that I'm going to go over next few slides is including total 19 storms with the 542 cases ranging from the 2022 all the way to 2022. And especially in 2020, pretty much add Gulf of Mexico landfalling storms. So that's what I'm interested in. This is NHC homogeneous verification, mean absolute error in the top two panels for track and the left and the V maximum on the right side. MUM6 coupling is in red, HAPS-A in green, and HAPS-B. When you see top track, MAE, there's no red lines pop up. It's just much buried under the HAPS-A green. And moving on to the V maximum MAE on the right side, that is slightly seen in red lines, but it's pretty much takes place in early lead hours, less than 24 hours, and then a later time, after 72 hours. So based on these two MAE, they're pretty much neck to neck, same. And then bottom two panel shows that P maximum and the P minimum intensity biases on the left side. MUM6 coupling is a little bit less under biased for P maximum compared to green line in the HAPS-A, but it still doesn't beat HAPS-B in early time shown in the cyan. And the P minimum, that is more red colors toward the longer lead time. This one might have to do with the storm size for MUM6 coupling compared to HAPS-A in cyan and HAPS-B in cyan and HAPS-A in green. So this, we did sort of stratified intensity for the verification, and then left column shows that weak winds, and the right one is strong. Top panel is MAE for intensity, and bottom panel shows that the bias for separate stratified intensities. So notice that the red lines has more variations on the weak storm compared to strong storms. Okay, next, this is a track. As you see, MUM6 has improved the track, especially for weak storm between the 48 and the 96 forecast lead time, but substantial improvement onward of 96 lead time in the weak storm. But in the strong storm, it's hard to differentiate between HICOM and the MUM6 coupling. This is one case study, and over 542 cases. Notice that the Hurricane Laura performs the worst among the worst storms. They are including Elsa, Henri, and Earl. So I picked the two cyclones of the Laura case. One performs better, and then and the best performance, but I show you later on. But this one is scale graphics on the right side, And then this V maximum on the right side, you can see that the intensity prediction for MUM6 pretty much under-predicted compared to HAPS-A in green and SB. And the bottom right shows that the track skill comparison. Notice that the MUM6 coupling is performed better early lead time, at least 48 hours compared to HAPS-A. And then this is 2 cases that I'm talking about. One case is the worst case, which is 6Z on August 24th, shown in as an green, blue for MUM6 and HICOM, and the red is MUM6 coupling for a particular cycle. And then 0Z on August 25th, 18 hours later, the second cycle that shows the best performance on the right side in the V maximum plot. Okay, so compared to between blue and then orange curves, that is HICOM coupling versus MUM6 coupling respectively. And then 0Z cycle on August 25th, green is HICOM coupling, and the red is MUM6 coupling. So these particular 2 cycles, and there are very different predictions take places. So this one is, since the ocean coupling is pretty much providing thermal energy to the TC itself, so I'm just looking at the thermal properties on a storm footprint at the 34 knots net radius on curves on each plot. And the blue is HICOM coupling, and the orange is MUM6 coupling for SSD changes, and the top left, and then left upper corner, and then sensible and the latent heat fluxes on the left column for cycle 0Z on August 24th, and the right side is the 0Z on August 25th. The shaded with the red line, red boxes representing where the intensities become really unsettled for especially MUM6 in orange, and then the bars are representing the mean of footprint of SSD change, sensible heat flux changes in the middle panel, and the latent heat flux changes on the left panel. So as you notice that the storm size for MUM6 coupling in orange is small, and yet the mean values is pretty much on the negative side, and the variation is quite large. Okay, so this is the thermal structures, temperature anomaly on a radial distance in x-axis in height, and then shade is the temperature anomaly, and then contours, dash contours, and then solid contours representing radial velocity. So this line is pretty much inflow, and the solid line is the outflow for every 6 hours from the initial condition at the top left. So notice that the initial condition already did quite different in atmospheric side for MUM6 on the left and the HICOM on the right side. And then there are warming takes places for MUM6 HICOM coupling, HAPS-A, and then it continues warming up next to 18 hours compared to MUM6 on the left side. On the right panel shows that maximum T anomaly locations in x-axis and then height. And the left one is MUM6 for this particular cycle. And then HAPS-A on the right side. I've noticed that all the dots showing that the HAPS-A HICOM coupling has a pretty much a little bit organized, pretty close to large temperature anomaly existing near the storm eye wall compared to MUM6 on the left side. It's more a little bit scattered around and then positioning in a lower altitude. And this one is 0Z on August 25th during the rapid cycle, but these are the forecast 24 hours all the way to 42 hours. And then the same temperature anomaly in the shade, and then radial velocities in the contour and the contour lines. So, during the rapid intensification, as you I shown that the prediction, intense prediction, a couple slides earlier, there are no differences between MUM6 coupling and then HICAM coupling. But as for structure change, in terms of structures on the right panel, it shows that again, high temperature anomaly pretty much towards sitting in a lower tropopause for MUM6 coupling compared to HICAM on the right side. Okay, so this is I alluded earlier for the MUM6 coupling, we need the CDAPs to take care of only forcings in area where exclusively not covered by the atmospheric side or ocean side. So this particular, oops, sorry, mine is not there. Okay, so this bottom three panel shows that mixed layer depths at the 96 forecast hours coming from HICAM on the left and the MUM6 in the middle, and the differences on the right side. So you notice that there are string distinctive line cutting across middle of the Atlantic Ocean. That is where the eastern boundary of the atmospheric domain sits in. So in other words, on the right side of the line is forced by the CDAPs from the datum. Okay, so on the left side, we continuously update all the forcings, and the feedback takes places at every coupling time step. So at the end of the day, they are quite different, and there is distinctive discrepancies in the not only surface field, but also, as shown here, mixed layer depths, they do have a different upper layer responses. And then concluding remarks, HAPS-A is insensitive to ocean model component, where tests are done for HICAM versus MUM6. Noted that both systems use the same initial conditions and slightly a little bit different boundary conditions for MUM6. However, the thesis structure is quite different, especially thermal properties. There is a significant T anomalies for HAPS-A HICAM exhibit showing significant contrast in a TC temperature anomaly, and the warming takes place is higher altitude, and then in a HAPS-A compared to MUM6 coupling. To support this finding, and we need a further analysis by including more cases. And then this is a challenge for UFS regional application. Again, I'm going to emphasize the datum applications for the area of non-overlapped by FV3 and the MUM6.
Thank you.
Thank you.
Thank you, Hansuk. And question, have one minute.
Is there any chance we could push the questions during the Q&A, since we're already over and we're going to start going over the break? Because we're going to have the Q&A when we get back from the break.
Andy, save your question later.
Is that okay?
Okay.
I mean, we can go ahead and do it, but
yeah, let's move
I
on.
appreciate it.
You know, I don't want to cut too much of your break time. Let's go to the next speaker, Shilu. Shilu, you're online or you're here?
Yeah, I'm online.
Okay, I thought you're here. So Shilu is from OU, University of Oklahoma. He will present DA related techniques. And Shilu, and the floor is yours. Go ahead.
Okay, so can you see my screen?
Yes.
Okay, great. So hello everyone, my name is Shilu. I'm a research scientist working with Dr. Shiguang Wang from OU. Today I'm going to talk about the simultaneous MDA, the multi-scale data simulation with scale-dependent localization, the SDL, for HAPS 4D environment. So before I move on, I'd like to give you this flowchart of a cycle self-consistent ENVAR-DA system for HAPS. So all those boxes were the functionalities or capabilities that is already implemented into the HAPS version 1. And the cyan boxes were the contribution from OU MapLab. And the purple box here is 4D ENVAR, which will be operational this year, which is a very good, exciting news. So let's go back to why we do the MDA. So why do we want to do the multi-scale data simulation? With our increasing computational resources and advancing technologies, the next generation numerical weather prediction models was able to resolve a wide range of scales for individual Earth system components. This is especially important for the hurricane predictions because hurricanes involves large-scale systems like the environmental flow that basically controls the track prediction, as well as the small-scale systems like the convective burst, which is directly related to the intensity evolution. So the next generation data simulation system is required to effectively analyze the state and quantify its uncertainty across multiple scales, which is termed as the multi-scale data simulation. And what is a simultaneous multi-scale data simulation? A simultaneous multi-scale data simulation approach, as opposed to a sequential approach, will allow all the observations to correct all the resolved scales at once. So the figures here shows an example. The simultaneous MDA we are applying is a scale-dependent localization, the SDL. So what it does is like when you define a separation scale to separate the system to be a large scale on the left and a small scale on the right, we can apply different localization scales. So for example, for the single observation at the red dot here, we will apply a larger localization scale for the large scale, and you see the increments from those blue vectors were larger on the left. And for the smaller scale, we can apply a smaller localization scale, which creates a more concentrated or localized increment pattern here. This SDL has been implemented and tested for the FRA3 GFS 4D and VAR and showed improvement on both global and hurricane predictions. And so what do we do here? In this work, we further extended this SDL MDA method into the HAS 4D and VAR. And here is an example of the one-op test. So the upper panel shows observation near the storm, and the lower panel shows an observation at the southwest edge of a subtropical high in the environment. So the observations were 1 meter per second merino wind at the green dots. So the left column is the small-scale single localization increments, and the right column is a large single-scale localization. And the middle column is, of course, the SDL. So if you look at the upper panel first, the large-scale localization tend to create those spurious corrections in those regions. And for the SDL, you can benefit from the small-scale localization that it concentrates the increments inside the storm range. Basically, it will create anticyclonic correction here. And for the lower panels, the small-scale localization was, the impact range was not large enough for such a large, subtropical high, the environmental flow system. And the SDL was able to benefit from the large-scale localization that it can create a reasonably large range impact or increments in this case. So those single observation tests show that the MDA with the SDL can simultaneously properly correct both the TC and its large-scale steering flow information here. And the experiments we designed were 3. So the 4DS using a small-scale single localization, which is at around the 180 kilometer cutoff radii. This is from our experiments with the inner core TDR-DA. And the 4DL using a larger scale single-scale localization at around 1,600 kilometers from the global GFS. And the 4D-SDL, of course, using an SDL approach, using 180 for the smaller scale and the 1,600 for the larger scale. So the separation scale was especially tuned for hurricanes at around the 100 kilometer here. And the domain is the black box here. Almost a basin scale is a single domain configuration, and we will simulate all the operational observations from HAFS or HROF. And the ocean is coupled with the HiCon ocean model, and we are still using the 80-member GFS ensemble in this study. So the self-cycled HAFS ensemble will be our next step. And the physics schemes were listed here. So let's look at some results. The lines here shows the mean absolute forecast errors during Hurricane Laura from the beginning to the end of its life cycle. The left column is the Vmax, minimum is the minus pressure, and track on the right. Red line for the 40SDL, blue line for the 40L, and the green line for the 40S. So if we first compare the green line and the blue line first, you will notice that the 40L outperforms 40S in almost all forecast metrics. So it's kind of within expectation that the large scale localization benefits the track prediction more. But why it's still better in, thank you. Better in the intensity predictions, we will explain that in the next slide. And if we look at the red lines here, it will outperform both 40S and 40L, especially in the intensity predictions. For the track predictions, it kind of mixed with the 40L, but it clearly outperforms the 40S. So first of all, what happens with the small scale localization? So in this experiment configuration, we are running from the beginning of the Hurricane Laura, which is, when the storm was weak and there was not much inner core observations available. So in such a scenario, the small scale localization in 40S was not able to leverage the nearby observations for correction. So it kind of like created some worse background forecast and accumulated with time. But when the TDR or the inner core observation kick in, so for example, this time the lower left is the 40S background. It kind of has about 50 kilometer dislocation in the background forecast as compared to the best track. And when the inner core observations was assimilated, it was able to correct the location, but the pressure field or the wind field were showing some dipole features, which indicates some inconsistencies there. And 40L and 40SDL was better. So that's the issue of 40S. And so let's come back to the advantages of the 40SDL. So first of all, we noticed that the improvement in 40SDL was significant. And here is an example cycle at the 6Z25th. So the red line is 40SDL, black line is best track. Clearly, the 40SDL was able to capture this rapid intensification better than the other two. And we noticed that it was due to the better warm core structure on the upper left panel here. So these were the absolute mean temperature anomaly, which indicates that the 40SDL has a better organized and warmer warm core structures as compared to the other two experiments. And this is consistently found during all the intensification period, which is average showing in the lower panel here. And the 40SDL was about 0.2 K warmer than the 40L and about 0.7 K greater than the 40S. So this indicates that the better intensity prediction from the SDL was due to better inner core warm core structure analysis. And how about the track predictions? So this is a particular cycle at the 12Z23rd. And we noticed that the green line, the 40S, have eastward bias, which results in a larger track error in the later lead times. So what happened is when we look at the analysis, this is a steering flow average between 500 and 900 millibar. And if you look at the zooming in boxes here, the black contour was the average, the geopotential height, and the thicker black line is the best track, and the purple line is the forecast. So the model forecast basically follows this edge of this southwest subtropical high. And when the 40S positioning the subtropical high more northward, the track later is also eastward. So this was elevated or better positioned by the 40L and 40SDL. So this results indicates that the better track predictions in 40SDL was benefited from the large-scale localization 40L. And those were for the analysis. How about the forecast? So this figure shows the RMC calculated against different kind of observations, and this is for averaged over all cycles. The upper panel is from the drop sound, basically describing the inner core, and the lower panel is from the rolling sound, basically describes the inner environment flow, and these were all verified against the 6R forecast. So if you notice, since this is RMC, it means smaller the better. So more close to the left, better. And you will notice that clearly the 40SDL, the red lines, were almost always left side of the 40S in green or 40L in the blue. This indicates that in both the analysis and forecast, the SDL was performing better in terms of the Vmax, mean pressure, track metrics, or as well as the warm core environment flow and all those kind of structural analysis or predictions. So a quick summary here. The SSL using a larger localization outperforms SSL using a smaller localization in almost all aspects in this configuration. And the MDA using SDL outperforms SSL using a smaller localization for both intensity and track predictions. And also outperforms SSL using the larger localization for intensity predictions. And the detailed diagnostic suggests that MDA using SDL produces better inner core warm core structure analysis that improves the intensity predictions during the intensification period. And the MDA using SDL produces better synoptic scale analysis, improves the track predictions during early period as compared to the small scale SSL. And the MDA using the SDL produces better forecast structures when compared to the observations at almost all levels as compared to both SSL. So here are some references related to the talk. And that's all for today. And I'd like to take any questions. Thank you.
Yeah, thank you, Shilu. And we save time, save your question during the Q&A. If you really right now you want to ask one question, I give you one chance. But more like an extensive question we want to during the Q&A session. Anyone? Online question, I think let's save to the Q&A part. Okay.
Okay.
Thank you. And we take a break, right?
Yeah, we're gonna be taking a break. The break should be over here at 11 o'clock. So we hope to see everybody back.
Yeah, I hope everyone stay. Especially you give a talk, you stay during the Q&A session. You might have questions for Eric.
Hi. So I'd like just to ask the last speaker to have a look at the Slido questions in the EPIC website where we have the live stream. There's a question by Dr. John Potter.
here. This is gonna be there.
I don't think your mic's on. You're just coming from your voice. Yeah, you're there.
Is it working now? All right. All right, so we're gonna go ahead and end this this part of the break, do our time constraints. This is gonna be the second half of the session for a hurricane analysis and forecast system. We have 2 more presenters, and then after that, we will be having a Q&A session. So if anybody wants to just hold their questions afterwards, I also encourage people to log into Slido or click on Slido and ask questions there. We'll be sure to get all those questions out to all the presenters. And if for any reason we can't get them answered, we'll find a way to get those answers to you. So without further ado, I'm going to go ahead and pass this on.
Okay, let's get started. The next speaker, John Portjoy from University of Maryland. He's a professor there. He graduated from Penn State. John.
All right, thank you. First, sorry for not being able to attend in person. This is my second conference in the last 2 weeks, and so I have to do this virtually. So this talk is going to be a bit different from the last few in that it's going to essentially discuss how my group is leveraging NSF developments to tackle outstanding problems for NWP, using halves as sort of a mechanism for doing this. And a lot of the topics we're going to talk about are tied to broader UFS problems, so not just halves. And so I have a number of awards to acknowledge for this presentation. Here we go. So the primary objective of our HABS-related research is to implement novel data simulation methodology that is immediately relevant for the hurricane application. Specific topics for this research include new developments for fully cycled ensemble data simulation within HABS, which is ultimately needed for doing strongly coupled data simulation in the long run, and doing a better job using satellite radiance measurements, treating sampling errors in high-resolution ensembles, and tackling outstanding issues for non-Gaussian error distributions. And I have 2 representatives at this meeting right now. 2 of my grad students are presenting this week. Joey presented yesterday, and Kente Kurosawa has a poster later on in the week to talk about some of the more details of this work. For me today, I'm going to mostly touch on this non-Gaussian part of our research and talk about how these advancements also bring about future advancements and spend a bit of time on more NSF-focused project that has relevance to the UFS. So one objective of our research for HABS is to explore implications of replacing the ensemble common filter with a localized particle filter, which is a non-Gaussian data simulation method. These techniques tend to be used for just updating ensemble members about an ensemble variational analysis, or ENVAR. And I have some motivation for why we may want to do this. So first, most prediction systems rely on ENVAR for very practical reasons. Namely, we have a high resolution control and usually a coarser resolution ensemble that's updated about that control state. The way we update the ensemble for ensemble data simulation is with ensemble common filters. And that provides the information for the next data simulation cycle for the ENVAR. And so the ENVAR part relies on an ENKF in some way to propagate ensemble error covariances forward in time. ENKF members are recentered on the ENVAR analysis, which has problems in itself, which I'll touch on. And so I'm going to use a very idealized example to sort of motivate our research on this topic. So say you have a 2-variable problem, and so you have 2 variables characterized by x1 and x2, and you observe one of these variables with some operator h, with some operator h mapped between that variable and the observation that you have. In very complex examples, H can be, say, a radiative transfer model for simulating radiances. In this case, if H is nonlinear, in this case, I just use the log function, you end up with this non-Gaussian DA problem that you have to solve, in which the error dependence between H of X and X could look very non-Gaussian. And so in this case, these blue markers are samples from some prior distribution that exhibits this, this type of behavior, and you sort of get this banana-shaped, PDF. We could, through brute force, solve this problem by using very large ensembles and a particle filter without any assumptions. And the red dots are what you would call the Bayesian solution to this problem. And so make no approximations, a really big ensemble, and we can outright solve this problem and draw samples from our Bayesian posterior, which we're trying to get at through data assimilation. The green X I'm showing here is the corresponding variational analysis. And so notice how the mean for this ensemble matches up quite well with that variational analysis. And the reason why that is variational methods can solve moderately nonlinear DA problems like this one through the use of an outer loop. In fact, that's one reason why the IFS is such a really accurate modeling system is they use an outer loop for the actual time window used for 40 bar. And so you don't have a strong mismatch between the red dots and this X. Now, if you were to use an ensemble comment filter to update these blue dots to reflect samples from this posterior in red, you get something that does not necessarily satisfy our initial probability density that we have. And so the result is not, within the support of the prior. And so we end up having is a bunch of samples that are drawn outside of this distribution. And if you were to go ahead and recenter these members on this X, the solution just gets even worse. And so this is essentially what we do when we do ENKF, ENVAR data simulation. The practical implications of doing so are you get very unphysical model states. And so what I'm showing here on the left is the output of halves for one ensemble member for ENKF for the 250 millibar vorticity field, just showing positive values. And on the right, the same solution, but for the particle filter. And so what you're left with is a ton of noise in your analysis, which is really just the ENKF pulling these members into unphysical directions, just like I demonstrated in this very simple two-dimensional problem. And that results in a solution that just has way too much noise in it. And so it's a major obstacle if you want to solve multi-scale data simulation problems such as this one. Has major implications for ensemble prediction as well, which is a whole topic in itself. What I'm going to share today at the beginning of this talk is just some simple comparisons using an ENKF bar and a PF bar DA technique in halves. Both systems use 40 halves members to update the ensemble about a variational analysis. And for verification, I'm going to show results from 2 weeks of forecasts that were generated every 6 hours. We spun up for a whole week so we can lose memory of the initial GFS solution that we started with. And we're going to verify storm features using NHD best track data and the synoptic scale features using Aero5. And so a quick verification. I'll start on the right. I'm showing just the main average root mean square errors based off of Aero5 as they're verifying truth. And the red values are the PF bar and ENKF bar is blue. What you see is for what I'm showing here, specific humidity, U component of wind and temperature, we get noticeable improvements when we use this particle filter to update the ensemble and feed into the ENVAR step. So pretty robust results for the environmental conditions. And if you come on the left here, I'm showing track and intensity of root mean square errors for a pair of storms that occurred during our test period from 2020, which were Hurricanes Laura and Marco. And you can see noticeable improvements in track as well. Another thing I want to note is here I'm showing values for max wind and SLP. And a notable finding is the ensemble tends to collapse on us with the ENKF because the model has to deal with all those physical inconsistencies that you get in the initial conditions, whereas we get a nice quasi-linear increase in spread for the LPF members, which you can see in these results, but they are more general if you look at large-scale features as well. Our group is currently testing this methodology in 2023 implementations of halves A and halves B. Preliminary results are encouraging so far for the LPFR, but not robust enough to share with this audience yet. And also note the thanks to the WPO Innovation for Community Modeling competition, our group is going to be funded to bring these developments into an hourly updated GFS configuration pretty soon, which will have hopefully long-term implications for TCs as well. And so what I'm going to do next for the last part of this talk is take a big step back and say, okay, say we have a non-Gaussian data assimilation system in place for the UFS. What else does that buy us in the long run? And so I'm going to start with just very general statement. So Bayes' theorem tells us, like how we can draw samples, potentially draw samples from this posterior density through this multiplication of a prior and likelihood. And so for the particle filter, the way we specify this prior is through a sum of delta functions, and so a very general way. And another thing this buys us is you can bring this likelihood into the summation here and apply it for each particle individually. And you don't need a fixed functional form for this likelihood. So for ensemble common filters and for variational methods, we use a Gaussian, and it doesn't depend on the state itself. But in reality, we're dealing with P of y given x, and so the distribution of y given value for x being the truth, and so we do encounter regime-dependent observation errors, which would dictate differences in these likelihoods, which is something that I'm tackling through some NSF work. To show what we can do for this, for specific problems that are comparable to atmospheric problems, I'm going to show a very simple example using Model 3 of Lorentz 2005 as sort of my test model. This configuration supports chaotic behavior. I'm showing the evolution of just one state forward in time, showing on the left right here in this video, and it's just characterized by these this large scale wave and small scale waves embedded within it. And I'm going to perform a series of data assimilation experiments using the same particle filter that exists in HABS right now for our work for the UFS. If you want to see more details of this method, check out this QJRMS paper. And so what I'm going to do is give this model a very hard problem, which is I'm going to have non-Gaussian errors for my measurements. And so I'm going to have a heavy tail distribution. I just have a cavity distribution for sampling my measurement errors, which I'm going to simulate measurements with. And I'm going to make it regime dependent as well. And so if I have a model state that's positive, then it gets a positive bias for the observation errors. If it's negative, it gets a negative bias. And this is a problem that we see when we do all-sky radiance data assimilation, for example, where you have different hydrometeors that have different scattering properties that give you different errors depending on what the true state is. And so it's a regime-dependent error, which I'm replicating through this example right here. And so let's talk a bit about what our current approach is for this problem. The way we specify observation errors for DA is we first assume that our observations are just some map between the truth and our observed quantity, which is given by H, plus some error. And that error is called the observation error. If we want to specify a distribution for our likelihood part for DA, what we do is we say, okay, for a given model state n, so xn, y minus h of xn is an epsilon n. And the distribution for our epsilon is all we need for characterizing this likelihood part for DA.
We got 4 minutes.
Got it. And so we already have an assumption here that this distribution does not depend on our actual true state. It's just something that we fix and use for any model state that we think might be the truth. And so that's one limitation we already have for ensemble common filters and variational DA methods. And the other approximation is we assume that it's characterized by a normal distribution. And so you really have 2 approximations that go in here. What my group is doing right now is working with non-parametric ways of estimating that likelihood. I don't have time to go into details of this, but the end result is you build up, based on a training set, what a potential distribution is for y or epsilon given a truth. And that all fits into a nice matrix that you can look up during data assimilation. And for the case of particle filters, just weight your ensemble members based off of these likelihoods captured through some training data set. A lot of very interesting stuff in here. Reach out and ask me questions after the meeting if you want to know more details, but I don't have time to go through it today. but I will show some results. And so this is going back to that problem I introduced with the Lorenz model, where I have regime-dependent non-Gaussian errors. And on the left, I'm showing different P of epsilon given X's. And so different distributions for epsilon for a set of different model states. And I can perfectly back out that nice, like bimodal looking distribution based off of this, this data-driven estimate of the likelihoods. And then feed that back into the particle filter and use it during data simulation. And so what I'm showing here on the right is the evolution of posterior mean root mean square errors for a function of cycle number for my DA experiment. Blue is using my estimated likelihoods, red is the true likelihood. And you can essentially back out, like something that is just as accurate as if you actually knew that you had this regime dependence and the non-Gaussian errors. And the bottom is the best linear Gaussian estimate. These ideas are very general. I have another case that I'll share very quick in which we observe the square of model variables, but don't know it. And so we don't actually know what our observation operators are. We still don't know what the distribution of epsilon is. And we also have 5 unknown parameters for the model. And so the objective here is not only to do state estimation, but do joint parameter estimation. And in this case, I can again back out something that is similar to knowing all this information. And so here we don't know the distribution of epsilon, we don't know our measurement operators, we don't even know what the parameters for the model. You can back out something that's very accurate. So just quickly summarize, we brought a new ensemble data simulation system into HAVS, which solves some issues with non-Gaussian priors. Early results are very encouraging. And it opens up the landscape for new research on this topic, which is probably the most exciting part of this work. Thank you.
Quick question. If not, I have a quick question, John, for you.
Sure.
Is your method easy to transfer to JEDA framework in the future?
I have a grad student that's transitioning into Dart right now. So Dart is much easier framework for developers. And so that's our first step in doing this. We'd love to bring it into JEDI with some hand-holding, of course. But everything I've done here is it scales for high dimensional problems by construction.
Okay. Yeah, if you have more questions, just save it. We have a Q&A session, 11:35. Let me finish my talk. My talk is more based on everyone's work and set up the...
Shujin, you want me to introduce you first?
Yeah.
All right. So Shujin is currently working for the NOAA AOML Hurricane Research Division HRD. And he is currently leading the NOAA UFS R20 hurricane application teams, and he obtained his PhD degree at North Carolina State University. Shujin, go ahead.
Thank you, Zach. And yeah, so I'm going to squeeze my talk a little bit because I don't properly handle the time. So punish myself first. Okay, so this is I'm going to talk about future priority. So here is the slide I submit to here. Look like this is not the latest version. Sorry about that, and that's okay. And I should acknowledge the STI also. The NWS STI, they also support all our effort. Move to next slide. Oh, you want? I can do this. Okay, here is the HAVS development approach. So we basically follow the same UFS community approach. So in the left side, we have the NOAA supported project. In the right side, the community supported project. Any of those projects can lay the foundation for our transition. Then some of those projects, their development can feed into our research to operation transition. So then our team implement those transition to operations and do the operational system implementation. And you already see that I don't need to mention HAFS now become a new operational hurricane forecast model. Next slide. Okay, this is the development priority after IOC, the initial operational capability implementation. So we have several, because this is a large team, everyone is working on the different aspects. So I lay down this, the whole team, especially the lead, co-leader Zach and Avichar, with me to lay down all these priority for the next few years. This is the new future. So we focus on first develop the moving nest multiple stones and the flexible nesting refinement that can give us much flexible the resolution for the model configured new configuration. Then the second part is the DA effort. We're gonna focus on the data in introduce more data and also self-cycle DA part. We have other project work on the weekly atmosphere ocean coupled DA, and also we focus on JEDI transition for the new future. And we also develop the ensemble capability, especially right now we are work on the Amazon AWS. So we are working on the stochastic physics ensemble capability and also the ensemble on the cloud. That's the engineering part. I heard they had a successful one just the past few days. The physics part, we're going to focus on the PBL for TC. That's always very big impact for TC intensity and structures. And we also transition to NOAA-MP. That is coming from the weather model. So we just follow their transition plan that we also transition. The CP, the convection scheme, that is one of the things we are testing because we have two configuration and our team work on the convection parameterization, upgrade, transition, and evaluation, use different convection scheme. Microphysics parameterization is one of the biggest impact physics part, especially the DA or the precipitation, everything is connected to microphysics. So we focus on that part and try to implement the GFDL version 3 microphysics scheme and also the Thompson scheme in the current version. We try to also improve that part. The ocean and wave model transition. So right now we are using HICOM. Then Hansuk just mentioned that she is working on the MOM6 and the transition to the operation when it is ready. And because our stakeholder is NHC, National Weather Center, and WPC, the Weather Prediction Center. So first of all, we produce the products for them because otherwise they can't use our model. So we have a team work with NHC to put the new products and try to improve the products fidelities. All this is in our portfolio to work on that. And we also try to move the current 5 days to 7 days forecast products. And its model is also need to go 7 days. And certainly the workflow always has the space to make improvement. Next slide. The future innovation. So some of the idea come from this team is the global moving nest. So that is one of the biggest push right now. We are working on the global moving nest, but it will take us a little bit more time to implement that. And another one is the telescopic moving nest for LES capability. So large area simulation capability. That is for research at this moment, but once we have that tool, it gives us a powerful tool to configure our physics to for DA, and everything, the dynamics test, everything we can use that capability. And scientists also can take advantage of this capability. And DA is one of our priority in the future. Especially how can we take advantage of the AI machine learning technology for DA? That is probably one of the questions. Daria will have more say about that. But this is also in our consideration. We have several team members. They understand and they are working on DA capability. So working on the AI tech capability. So we're going to gradually introduce those AI technology into DA. And the ocean atmosphere ocean coupled DA. That is, we're still testing whether we want a strong or strongly or weakly couple. All sky radiance, that certainly is always the DA group, their focus. But one of the questions I asked is, we are using CRTM in the DA scheme, but in our model, we are use TMG. Whether we want to combine, we can combine these two radiation transfer model together, so that we can have much more straightforward simulation, direct simulate the radiance. That is still question mark. I don't know the answer yet. The new DA methodology, that's like today, Xu Guang mentioned the multi-scale or scale aware DA. And John just mentioned his particle filter, etc. All the DA new methodology we are working, and we are we're willing to work with them to test in our model. And the reason to do this is that any of those DA method in the hurricane environment is much more prominent impact. If we do the weather model, maybe not that prominent, but at this moment we focus on the hurricane, we maybe have the bigger impact immediately. And the DA and the physics parameterization interaction, we always have that debate whether DA or physics screw up some things. So we want to explore this interaction, especially when we change the physics, and we also need to probably adjust our DA strategy. Next slide. Oh, sorry. Do I have one more? Yeah. The other things we are focused on, that's under the HFIP, we have the observation. We have new observation, test new observation, especially from the US and this cell drone. All those data we collected, all those can test in our model. And also we have connected with the Aussie team. They do the observation strategy test. These like in different group, but we take advantage of their discovery or their results. And the ensemble, certainly, one of the things that we haven't done yet is the initial condition perturbation. That part we haven't done yet. We are focused on the physics, stochastic physics, and ensemble for DA. Certainly, that is one of the things we gradually transition to the future DA method. So ensemble on cloud will continue. Right now, we are still in the development stage. We will continue this in the next several years. The physics, several projects we are working on the physics parameterization. One of the is actually is myself. I'm leading that. Okay, work on the AI technology. Then the sub-kilometer physics. We have a talk in the afternoon about the 3D TKE supported by JTTI and the physics interaction. Certainly the ocean wave atmosphere, we already have atmosphere coupling. We already have that capability, that three-way coupling. The coupling strategy, we also need to think about whether we want the common grid, we want to do the interpolation between those different model grid. And the ocean and wave physics part also have this a lot of space to improve. Just like I heard from Hansuk, talk about the ocean, the mixing layer, mixing layer scheme like KPP new implementation. Those like all the focus on ocean model itself. Certainly Wave have the same situation. Then how to initialize the ocean and wave model, that is another bigger effort we need to push. So this is I just show you the nest capability we're gonna develop. Right now we have the, if you see, we have the second nest right now to focus on that as a TC area, and the outside is, you can see from the color code, we have the ocean model, we have the wave model. So then the black domain is the atmospheric model parent domain. And our future plan is to use the multiple stone in one basin. So that is one of the big efforts we are developing and the supplemental. And Bill Lemstrong will talk about this. And we also, I want to do some advertisements in the afternoon. We have the dynamics and the nesting. We have the dynamics and the nesting session at 3:15 to 4:45, and we also have this 7 more talk post talk in the post session. So welcome to go to all those talks and then find the author expert to talk about that. That's all I want to show. One more thing is our release plan. So if you want to go to the detail, then just look at this. This last slide, all the PowerPoint will be online quickly. So we have the plan to release, but schedule we haven't decided yet. And we have a scientific issue. We'll find published on Frontiers in Earth Science, and welcome everyone. If you can contribute, just go ahead and contribute to that. The QR code is here. You can scan it and go to that website. This is our team. This all the work attribute to our team. For that, thank you so much to stay with me, and let's start the Q&A session quickly. Any questions for me?
Well, if you don't mind, can we go ahead and I guess start the Q&A questions with at least one of the online questions, and then from there we can go to in-person questions.
Okay, so
So yeah, I would be reading the online questions, so you're not weighed upon too much on your duties. So the first online statement, it's not exactly a question. It was brought up by John Potterjoy. And before that, I'm actually Enrique Alves. I work for the Weather Program Office in the EPIC program. I think I need a little bit of introduction there. So John Potterjoy, he makes a statement in which he says, I understand that there are DICOR issues that are motivating a change to impasse by some of these groups. So John, is this a statement that you need clarifying or a question that you would like to have addressed by any of our speakers?
Yeah, so it was actually a question followed by a statement, but I think the question got removed. Could you guys hear me?
Yes, we can.
Yes.
John.
Can you hear me? Yeah.
Yeah, go ahead and rephrase your question, then I ask Kun. Kun, are you online?
Yes, Xuejin. Yes.
Yeah.
Yes.
I
Okay.
ask Kun answer your question.
Yeah. So my question was, it looks like a lot of your results have really major implications for the convective scale applications. And I mean, it's too bad that there's a parallel session going on right now where all those talks are separate from ours. But there are actually a couple of talks that directly focus on issues with the FP3, DICOR for their specific application. Are you familiar with some of the issues that they're raising, and do your results address some of these problems?
I'm glad you bring this up. So now, generally speaking, in high resolution convective scale model, the behavior of convection are controlled by a number of factors, right? In my talk, I mentioned it's implicit diffusivity associated with the convection scheme. But there are other factors that could have similar impact. And these factors include the explicit diffusion or the parameterized horizontal diffusion, and also the physics, right? Especially the convection parameterization. And the simulated characteristic of the convective motions are really controlled by the collective effect of those factors. Now, in my talk, I didn't intend to argue which scheme. I showed result from two schemes, HRD5 and HRD6. I didn't intend to argue which one is better or make any recommendation which one to use for high resolution model. In T-shelled and halves, we both use HRD6. We're getting very good results. But at JFDL, we also have another high resolution configuration, so-called C-shelled. And that one is for severe convection prediction over continental US. And this model does use HRD5. And it shows very good performance in capturing the characteristic of the convective events. So HRD5 is not necessarily unsuitable for convective scale models. Now, you mentioned there are some dipole issues. I'm not sure what these specific issues are, but my comment is that be careful with some wrongly intentioned argument floating around. This has been happening since NGGPS phase 2. The devil is in the details. I'm only loosely aware that there are some bad intentioned people manipulating FA3 to get the results they want to see. If there were issues, we hope they can talk to us directly so we can have a discussion, or have the results published so we can comment on it. But to my knowledge, that hasn't happened yet. So.
Okay,
Yeah,
so I'd like to just jump in there. Thanks, John, for the great question and the answer. We have quite a few questions. So, John, would you be okay perhaps to follow up on this discussion offline, and then we can go on to the next question?
Oh, absolutely. Go on.
Excellent. Thank you so much. So I'll pass it back to our chair.
Yeah, the next question, Ak.
Oh, okay.
Thank you, Kun.
All right, thank you.
Yeah,
Can you hear me?
Go ahead.
Yeah, can you hear me? Yeah, okay. Just and then we'll go to Slido. Sorry to just jump in here.
So just a quick organizing thing. Every questions in the room should go to Mike. I will be organizing the Slido questions.
Well, and we have our moderator that's standing up here as well. So
let's alternate. Online, in-room, online, in-room.
Perfect.
Yeah.
So I was just going to do something kind of big and suggest that Hurricane is essentially a regional model with a moving nest. Now that is really what is happening. The one thing that I'm really concerned about is to making sure that there's a connection between physics, that's in a non-moving nest and in the moving nest, and a consistency with physics in the regional versus the global scale. Because really, a boundary layer is a boundary layer. It just happened to be in a hurricane situation, very unstable, very high winds, et cetera. So, I'm kind of asking the audience here and then online, how do we accommodate that? How do we think about that in the future? I know certainly understanding the scale dependencies is really good. And I know Catherine Newman here at DTC and NCAR is in the room, and she is certainly, and others have addressed what is that scale dependency of the physics. Really important to understand. And then the one other thing that I like to play around with a single column model. Why? Because it's a great place to initially stress test your parameterizations. Yeah, it's not the whole solution. It can't be, because there's inherently 3D things going on, for goodness sakes, in a hurricane. But you can certainly find out and stress test parameterizations by giving it very high wind speeds, free convection, et cetera, very unstable, just to see what the behavior of the process is. Because the last thing we want to do is have a parameterization in, and then we find out, whoa, when you kick it up to 55 meters a second, something starts to break down. You can do that so inexpensively if you deal with much simpler pieces. Yes, part of the hierarchy that I'm always like to be pointed at. So anyway, I'm kind of posing that to the group, and wondering if any of the authors or any people in the audience here or virtually can provide any comments inside on that.
So please, let's keep any answers as brief as possible and
Yes.
provide a possibility for following up with the person who's asking. Thank you.
Yeah. Zach, do you want to respond a little bit? Zach?
Sure. Yes, sure. I mean, so currently we are actually in HAPS. We are testing different, actually, this is actually the reason why there are so many physics schemes floating around. So this probably deal with the different situations. For hurricane situations, we found that certain PBR schemes more, even though they have PBR is a PBR, but hurricanes often occurs over the oceans. So that's the other differences. And also sometimes we found some of the physics schemes may be performed better than others in some certain situations. For example, the weaker storms or stronger storms. That's why we needed the ensemble forecasts. I guess that's my response.
Yeah. Again, I guess I'm concerned that, this is a PBL for hurricane is perhaps not the right approach to take. It may behave better, but the point is, what are the ambient conditions that you have? Because wind speeds for boundary layers can go from, 0 to 55 meters a second, say, and you can have different stabilities and so on. I guess I like understanding the uniformity of physics and how they apply across the scales. But, well taken. I was at EMC for a number of years, and you can have a theoretical answer that may not necessarily address getting the hurricane right. So,
yeah, I quickly respond to that. Physics is universal. However, physics parameterization is not universal.
That's a good way to put it. So, Enrique, do we have an online question?
Yes, we do have a few online questions, and we're actually discussing the best way to address them. So what we're going to do, just to be fair to everybody who's asking, as well as everybody who is presenting, we're going to skip some of the questions. So say, for instance, John Potterjoy, he made a question now, has a few questions, but, please don't be offended. We're going to skip who has either asked the question already, try to come back to the end to these questions, or who has already answered a question. So the next question is from Jason Sippel for Hyunsuk Kim. The question is, did you notice any difference in storm size or precipitation as a result of MOM6? So this is a hot topic. We look forward to Hyunsuk's answer.
Jason, you asking me too much. I'm oceanographer, so I have not looked at any other details, atmospheric forecast side. But as for, I can definitely say about the storm size, and then MOM6 simulation produces smaller storm size. I've seen it. The bias is smaller. Quickly, it becomes a negative bias, and then MAE again, it's a little bit larger and tended to be not. It's a smaller. MAE is smaller, but other than that, it just first set of simulations. I have a lot of work to do. I just finished it, this presentation 1 week before this workshop. So they got a lot of work to do too. I'll keep you posted, Jason.
Thank you.
Like,
And any
Yeah.
response in the room? Here we go.
Okay, good question. This is Said Moghimi. I'm from Storm Surge Modeling Team, National Ocean Services. So obviously, I'm going to ask question in regard to storm surge models. So we had this conversation before. I was looking into the plan specifically for question is directed to you. In terms of we see like as a part of Coastal Act project also that inundation reduces the roughness, surface roughness, and that could drastically change the wind speed and the feedback mechanism. And we had this conversation before that when you have or thinking that the right time to also, when you have a landfalling system, start to also running a storm surge modeling and have the feedback of water surface elevation into the HAF system. So that's basically the question. Yeah.
Anyone want to respond? Yeah. Avichal.
Hi, Said. Yes, so this is Avichal from EMC. That's a great question. And as you pointed out correctly, we had hopes to continue our investigations as part of the Coastal Act to address this. And in my mind, I'm involved in a project working with others at NHC to look at the impacts of dynamical model inputs like HAFs onto operational storm surge models. But to do this correctly, we need to augment our coupling and bring in flooding and inundation capability into the HAF system. If it needs to happen with an additional modeling component, so be it. And I would also say that another important aspect of this is going to bring in freshwater inflow, which means that some part of the national water model or some other community-based systems like Schism could play a role in future of HAFs. Thank you.
Sorry, I didn't mention about you. I will send you a questionnaire. What you need? I will send a questionnaire to you. What you need? Okay. Yeah.
We should
Let
look.
Hans, let
Is
Hans
that an answer?
respond. You want to respond?
It's an answer? Okay.
Yeah, Hans, go ahead and
Okay,
respond.
so Avichal has mentioned about the other non-hydrostatic model too, but in this storm surge case, we also need waves coupling too. Usually swell tended to moving fast forward and arriving in the coastal area. So we have to also considering wave coupling too.
We only have 10 minutes, less than 10 minutes now until the top of the hour. So if you could take up the discussions offline, we still have like about 4 or 5 questions online. I'll go. Yes.
One quick programmatic response to that question.
Sure.
Is this mic on? Okay, it is. All right. So Saeed, I just wanted to respond to your question because it affects both programs that I manage, Coastal Act and HFIP. I wish we had a solution where we could make Coastal Act come back and actually be treated like it should be. But as you well know, we don't right now. There are other avenues that we're trying to look into within OSTI modeling with doing at least some of it through the UFS coast. It's just there's a lot of moving parts that have to be figured out because we can't just take Coastal Act away since we're still congressionally mandated. But yeah, so any information you can give to the various teams is definitely greatly appreciated, and we can use it hopefully to move forward.
Yeah, to be fair with Saeed,
Yeah.
since
Move to
I
online.
allowed you to jump in. Saeed, would you like to make a quick remark? Okay, just to be fair with you.
So will we be capturing all these things in Slido and they won't be lost and somehow they can be conveyed to the broader group?
Yes.
Okay, go ahead. Next one.
So we'll jump into the next online question. It's a question from our virtual chair, Zhang for John Martinez. So John Martinez, if you're in the room, please, if you can get the microphone off Mike Eck, and I can make the question. Oh, you're here. Okay. So I'll make the question if you want to get the microphone. So just go on directly to you. So the question is, you mentioned the operational TCVN, ICVN will include HWRF and HMON. Will NHC, National Hurricane Center, produce consensus models in which HWRF and HMON are not included?
Yeah, maybe I have a clarification question based on that. So in operations this season, we're going to have the 4 models forming or part of the consensus aid. So are you asking if there will be another version of IVCN, for example, that doesn't have HWRF and HMON?
Yes, that's correct. Yes, that's my question.
I would have to double check with the forecasters and how that's sort of developed in real time in ATCF. My understanding is that it's relatively straightforward to just create whatever consensus you would like in the ATCF. So they could have a version operationally that just has the 2 halves models. I don't know if they're going to be doing that though.
Yeah, because the reason I ask is this is because sometimes both HWRF and HMON will running operationally in reduced capacities. It's only maximum 3 storms. So in some of the TCVC, the consensus models were not included, and some of them were included. So that for fair comparisons between the HWRF and HMON, it will be better to produce 2 sets of the IVC, the consensus models.
Yeah, so I think in real time, the consensus aids are developed as variable consensus aids. So whatever's available to them, they're going to use. So if HAFS isn't available for some reason because of limited capacity, then and HWRF and HMON are available, or vice versa, it's just going to grab whatever's available. But yeah, I definitely follow your remark in terms of a fair comparison. Like you don't want to use IVCN with the 2 halves models and then use another version with HWRF and HMON when maybe HWRF is missing, or vice versa, like maybe one of the halves model is missing. So in terms of doing the verification follow-up in the season, we'll definitely keep an eye out for that. We do everything offline for the verification anyway, so we take all that into consideration.
All right, thanks.
Thank you. Back to the in-person questions.
Yeah. Question in the room? Yeah, it's on.
Okay. So somewhere in your talk, you said that HAFS is one of the future things you need to do is to account for multiple storms in the basin. So I saw that you have a few moving nests, but my understanding, I'm not an atmospheric person, is that proximity of the storms means that the storms interact together and some kind of special physics are involved. So what are these physics? How are you accounting for these physical processes? And what kind of physical processes we have? I'm asking this question because we're developing a parametric hurricane modeling system at our branch that generates the atmospheric fields from storm tracks. Okay, and one thing we need to do is we need to account for multiple storms in the basin, like for example the ones that appeared 2 years ago in New Orleans, that hit New Orleans. So this is one question. The other question, PBL versus PBL for TC applications. What's the difference?
We have in the room and very helpful questions, and I let them answer you directly.
Yeah, so in terms of multiple storms, so I'll be giving a talk this afternoon talking about implementing 2 and more nests. I think some of the main things that are the physics interacting between the storms are, for instance, the outflow from one storm can suppress a weaker storm nearby. There also could be some interaction where that outflow, affects a nearby high pressure system and changes some steering for other storms. So, you know, we want the resolution to resolve the storms correctly at the right intensity. We don't really have to add new physical parameterizations once we do that. But I think the problem you have when you're running only one storm is if you have another one that's far away in the basin that hasn't really developed to the right intensity, then you have, you know, incorrect forecasts. So I think that's sort of the main way that those will interact. Sure.
So why YTC was? Oh yeah, so I think like yeah, that's a good question, but actually almost all physics are not designed for high weekend applications. So that's a challenge here. Like even we find some suits of physical works well for some forecasts, but we really don't know actually. So for the physics part, yeah, we have large area simulations to so basically our idea was try to using the in situ drop zones to nudging to fix the thermodynamic conditions, and then to constrain the hurricane like gradient wind balance, the dynamic constraint areas, and then provide some reference. So that's what we do. And for the TCPBL, yeah, to answer the question before, like whether it's applicable outside the domain. So what we do now is we apply this for the moving nest. So that's mostly just for the hurricane environments right now. But I agree in the future, it should be a unified physics that can applicable to all the conditions. So MOI, like some other scheme, are doing the job like now. So we work with Joe also to test in the MOI in the hurricane conditions. So that's the current job. Hopefully answer your question.
Yeah, I think you know both of the experts. So if you want a further discussion, go direct to them during the lunchtime. And last question go to online.
Okay, thank you so much. We are really at the top of the hour, so I will have one more question. I do encourage everybody who has posted questions on Slido to keep an eye out, because we are asking all the presenters to review the Slido questions. So please, presenters, review Slido questions and provide replies online through Slido, or if you want to reach out to each other. Everybody pretty much knows who is who. But the question comes from our virtual presenter, virtual chair as well. And it's a question to Shu. Do we have to conduct DA, data simulation, for the entire HAFS parent domain in order to get benefits from SDL? I love the acronyms. In HAFS V1, DA is applied only for the nested domain. So would you be able to answer that question?
Yeah, sure. So this is a great question. Actually, I did the response on the Slido, but I can do it here as well. So yes, it's kind of like we imagine the SDO can benefit more from the larger domain, because larger domain covers more scales. But even for a smaller domain, like a nested domain, it should still be benefit from the as long as the hurricanes involves the across scale interactions, they have impact from the large scales, impact from the small scales. So as long as your domain is covers those scales, the SDL should still be working. Yeah.
All right, thanks, Xu.
Okay, so yeah, let's stop here because everyone hungry, and I don't want to cut off your lunchtime. And you can do further discussion if you want to stay room, discuss, that's fine. And if you want to go lunch, grab lunch, then sit together, discuss. That's really productive and wonderful discussion. Thank you, everyone.
All right, thank you, Xu.
I also want to remind any
I've been working as a working group, or the real working group, for a long time, and a lot of contributions that went into UFS or can be attributed to this dynamics and nesting, because it's the core concept of the unified forecast system. And the HAFS implementation is another success story you already heard many times. So what we are going to do here in the next remaining part of the session is to go through these presentations and then open up for some discussion. The first one will be by Lucas Harris, who will be talking about the worldwide federated FE3 community. Lucas, take it over.
Thanks, Vijay. Do my slides show okay?
Yes. Yes.
Okay, fantastic. Okay, so first I want to thank the FE3 team and our community collaborators who have contributed many of the results that I'm going to show here. I also want to mention that much of this work is being funded by the NOAA Research Global Nest Initiative. You can find more information about that at the site below. So just to review, FE3 is a GFDL finite volume cube sphere dynamical core, the fluid solver or engine for a large community of atmosphere models around the world. It's been developed with several different ideas in mind: high accuracy, physical realism, flexibility to other components, including physics in the ocean, and to be computationally efficient. And as a result, you get a lot of different advantages out of this. You get some of these very frontier high-resolution models, many applications from microscale to paleoclimate. It helps accelerate development, and it gives you timely forecasts as well. So here's a great example of the beautiful animation made by our partners at NASA, where FE3 was originally developed, in fact, showing carbon dioxide in the high-resolution NASA GEOS model. So yeah, there is a worldwide FE3 community, both here in the United States and abroad, and many different centers are using FE3 in their models. One of the great advantages of FE3 is that it's a federated community. You can easily take the dynamical core and tailor it to your particular agency's mission. So indeed, we have our collaborators at NASA for the weather and climate modeling and for planetary atmospheres on Mars. Our partners at Harvard University, who work closely with NASA on the GeoSchem high performance community model. Our partners at NCAR, Chinese Academy of Sciences, Central Weather Bureau, and most notably the NOAA unified modeling approach, where the two major models, the unified forecast system for weather applications and the GFDL seamless modeling suite for climate applications, all are powered by the FE3 dynamical core. There's a lot of reference information about FE3. You can go to the FE3 portal and find a lot of our peer-reviewed publications, technical documents, and tutorial presentations. In particular, this comprehensive scientific documentation that was written a few years ago that describes FE3's algorithms and usage in great detail. We have a public-facing GitHub. This is our public community hub for FE3. You can find the source code, official releases. You can do issue tracking, questions and answers. People can submit merge requests for new codes. There's additional documentation, these examples showing basic FE3 capabilities, and much more through the community GitHub website. So this is a really great resource I encourage people to check out. So what can you do with FE3? So here's a great example. So after we started getting involved with developing the UFS, we took FE3, we coupled it to the then GFS physics, and we started developing it holistically, physics and dynamics and everything together to make a better model. And after a few years of development, we applied it on the 2017, the very active hurricane season in the Atlantic, and we found that we were able, with our new experimental model, we now call SHIELD, to be able to improve upon the existing GFS. We didn't just stop there. We went to our partners at the European Center, and they gave us our initial conditions to be able to run within SHIELD. And we took that and we ran them. We ran using forecasts initialized from the European Center analyses, and we found that with those better initial conditions, we were actually able to beat the European Center in terms of hurricane track. So this led to two things. First of all, led to this dynamosic intercomparison led by the European Center. We just published a really neat paper in Earth and Space Sciences on an intercomparison of models, all using the European Center's ICs and their hurricane tracks. And this also set off a flurry of innovation within NOAA. broad effort by the broad NOAA community. FE3 is moving into operations. There's a big effort to improve the GFS's physics and the data assimilation. And the results are what you see here on the right, where the GFS has substantively caught up to the European Center in terms of tropical cyclone track prediction, and in 2021 actually beat the European Center in Atlantic track for the first time ever. And there's even more advantages coming down the pike, as you see with our experimental model Shields results. And I definitely want to give a shout out to the work that Fanglin, June, Daryl, and their teams are doing. They've really done a phenomenal job. They've improved the GFS so much over the years. They've really made it into the world's foremost free and completely open global weather model. And it's a really amazing resource for the community and a great achievement by EMC, and which I like to think we made our own little contribution towards. The community has also made a wonderful effort to improve continental convection in FE3-based models. We were told last fall that there is this issue with heavy precipitation in the RRFS. So our team, we got down, we took a look at what we could do. In particular, my colleagues Kai Ching and Lin Zhangzhou, they upgraded the microphysics in our own continental convection model called C-Shield. They've tuned the microphysics. They used it. They improve the interactions with the dynamics, and used a less diffusive advection scheme, and the results show off. Not only have we improved the storm structure an awful lot, in particular we have these beautiful precipitating anvils, but also we basically eliminated the heavy precipitation bias in C-Shield. So this is really a great example of what we get when you holistically develop a model, physics and dynamics together, and that's really how you get advances, developing things holistically as a whole. Which I know is a little redundant. You can also take a look at the excellent results by our partners at the University of Oklahoma at CAPS. They are some of the world's leaders at convective scale prediction, especially for continental convection. They've done amazing results with radar data assimilation and also with Lightning DA. They've shown some really amazing improvements in a forecast with that data assimilation in the SRW application, and that really shows the way forward. And again, the value of developing everything together as a holistic set, including the data assimilation and just the things that you can do. It also suggests that if you really do want to improve convective scales for prediction, the most important thing is try to look closely at your microphysics and make sure it's set up right. Now here's something really cool. Back in the before time, I went to the European Center and I met Tim Palmer. He was hearing about our nesting and other variable resolution capabilities that FE3 gives us. And he suggested that if we really want to improve S2S prediction on the United States, don't put a nest over the United States, put over the maritime continent and try to improve the MJO there. And already in GFDL's models, we get a pretty good MJO. In our Sphere climate model, in our Shield model, we get 25+ days MJO, even at 100-kilometer resolution, pretty coarse. The key is having a good convection scheme and a good ocean. But as you go to increasingly high resolution, that gives you better and better forecast the MJO. We have this collaboration with AOML. It's funded by the Global Nest Initiative. We developed this nested grid model, 16-kilometer global, 4-kilometer over the maritime continent. This is still a fairly efficient global regional nested model. And when AOML ran the results, we found that, yeah, it gives us a full 39 days of useful predictability, which is a really cool thing that we can do with this sort of nested model. And that comes partially improvements at the higher resolution from precipitation and that diurnal cycle over the maritime continent. And this also shows the real power of these variable resolution approaches towards S2S prediction. We have a separate project with NSSL to look at severe storm outbreak S2S nested prediction as well. FE3-based models have been the leaders in global storm resolving modeling for 15 years. The first US GSRM was a NASA GEOS, one of the first applications, in fact, of the CubeSphere version of what became FE3. It really benefits a lot from FE3's accuracy, efficiency, robustness. And in particular, lately, we've been able to do these really awesome years-long simulations, not just in the present day, but also in warmed climates. So we can start to do, this is the advent of convective scale climate simulations. Our partners at DOE developing the screen model. You hear about more from Paul Ulrich next. They are working on this as well. We got some really cool results we published already, studying convection, both in present day and under warm climate again. We're looking into water resources. One really cool thing is our partners at the Allen Institute for Artificial Intelligence. They have this very hungry machine learning algorithm they train on X-Shield output. They use it to correct a 200-kilometer GCM based on the FE3 GFS, an early version of the GFS. And they find that training on this very high resolution model, but running at very low resolution, 10,000 times cheaper, really improves a lot of problems with climate models. It greatly improves precipitation, the land diurnal cycle, surface temperature, and so on. So this opens up a lot of possibilities for really studying climate impacts of certain extreme events. We can go even farther than that. This is a line I've stolen from Richard Feynman. There's plenty of room at the bottom. So he was referring to nanotechnology. In this case, I'm referring to atmospheric microscales. But we can do some really cool things, again, with FE3-based models. Here's one of my favorite examples. This is something we've been working on for a while now. We were able to do a super stretched model, global model, over to a small area down under 1 kilometer very efficiently. And we find that we get these beautiful splitting thunderstorm, but also due to FE3's excellent representation of rotational modes, we get these interesting features below cloud base. And these are dynamically like tornadoes. They're a little bit larger than real life tornadoes. You can't resolve tornadoes at 1 kilometer resolution. So we call these tornado-like vortices. This is a really, really neat thing showing some of the power of FE3. We can go beyond that. We're looking into multi-nesting, model called Teleshield for hyperlocal impacts, in this case over the Northeast Corridor region. Looking into large eddy simulations. Here's a case of 35-meter forced shallow convection, basically cumulus convection. And we've been looking into large eddy simulation, or not, radiative convective equilibrium for a while. And this is the ultimately weakly forced simulation where there's no shear whatsoever. And not only is this useful for research on convection, we also find this interesting thing that convection in FE3 collapses to grid scale at these scales. And this is the same as what a lot of other convective scale models get as well. And we also see convergence being able to represent some of these entraining features once you get down to 250-meter resolution, which satisfies George Bryan's criteria for convergence. They see that in other models as well, like CM1. So there's a lot of things you can do when you get to these increasingly high resolutions. One of the best things about working in NOAA is I get to work with some of the best scientists in the world, and there's a whole hive of activity around FE3 that we're really excited about. You can see a lot of different projects here, some of which will be talked about in this session. I want to especially call out Oliver Elber's talk. Unfortunately, it's in the system architecture session right now. But yeah, we're working with the Allen Institute with a number of different international collaboration to port FE3 for GPU acceleration. They've published a beautiful article on this earlier this year, getting some really amazing accelerations on GPU systems. And there's a lot of other these projects that are coming down the pike as well. So it's really, really exciting time. Finally, a few things about community and cooperation. Again, yeah, we got a great opportunity to work with some of the best model developers in the world. Both people who are using directly using FE3 as well as cooperating with other model development efforts. In particular, I recommend checking out Paul Ulrich's talk next on the excellent Scream model. FE3 really benefits a lot from its different capabilities that, again, from microscale to paleoclimate, that allows exchange of ideas between all these different specialties, crossing all these scales and allowing exchange of innovations and development. One thing I do want to point out is that, yeah, community is a two-way street, and that's a really important thing. I think it's most succinctly said by this quote here by Morris Bender, who was the godfather of a dynamical operational hurricane prediction here in the United States. He developed the operational GFDL hurricane model for many years. And the way he put it, a key element that makes collaboration successful is having individuals who enjoy working together and are able to do so. And I think that's really the defining meaning of community, is just people who can work together and either develop together or learn together. So there's a lot that can be really made here by keeping this idea in mind. And finally, I want to thank the team of excellent people that I work with and our excellent collaborators, both inside and outside of NOAA, as well as FE3's creator, S.J. Lin, who retired from NOAA here a few years ago. And I think the results really bear out this quote from Steve Jobs. There are no shortcuts around quality, and ultimately quality starts with people. So that's all I have. Thank you very much. And this is a wonderful session. There's 5 more amazing talks ahead of us, so I definitely encourage you to stick around for those. Thank you so much.
Thank you, Lucas. Interest of time, let's save all the questions to the Q&A session. Write down your questions or send it to the chat, then you save that question, you keep your slot there, question slot there. Okay, thank you. Next talk is from Professor of UC Davis, Paul Ulrich, right? Paul,
Yeah.
are you? Yeah.
Yeah, I'm here. For some reason, oh wait. Oh, you asked me to start my video. Okay. It originally was saying I was not allowed to start my video, so I'm glad that you've given me permission. Right, let me pull up my slide deck.
Go ahead.
All right. I assume everybody can see that okay?
Yeah.
All right. Thank you very much for the introduction, Lucas. I remember actually back in 2016, I was down at NASA Ames giving a talk on atmospheric dynamical cores. And at the time, they were trying to decide which dicore to actually use for the next generation Mars GCM. And I put in a good word for FV cubed. I'm not sure if it actually affected anything. I don't think I have as much clout as I probably think I do, but I'm really curious actually how that decision came down the pipe and if my influence had any effect. But anyway, I'm not talking about FV cubed here today. I'm talking about the SCREAM model, which is the simple cloud resolving E3SM atmosphere model, which in my opinion is a great acronym. There are certain folks in DOE that are less enthusiastic about it, but they couldn't think of anything better, so we stuck with SCREAM. And so just continuing on the theme of dicore development, on the DOE side of things, of course, the SCREAM model itself is based on the high order method modeling environment, HOMME, which is a combination of finite element methods that are used for global dynamic simulation. And in particular, in SCREAM, we're using the spectral element dynamical core, which is a fourth order numerical method for solving the Navier-Stokes equations on the sphere. And then we wrap that around a lot of the infrastructure that went into the energy exascale Earth system model, or E3SM. The goal of the SCREAM project is basically to try to keep the code as simple as possible. And the goal here is to ensure portability between CPU and GPU infrastructure, again, taking advantage of Department of Energy investments in supercomputing systems. And so that's really paid off, I think, for us. On the right-hand side here, you see the number of simulated days per day for a 3.25 kilometer global grid spacing simulation, really down at the global cloud system resolving scale. And we were able to achieve, using basically the full allocation on the Frontier supercomputer, 1 simulated year per day, or 365 simulated days per day on that system with the GPU-enabled version of the code, which is pretty cool because with 1 simulated year per day, that's pretty much the threshold for doing kind of longer climate run simulations and investigating the climate that is being produced by this model. It's, of course, not quite a cloud resolving model, but that makes for a better acronym. Again, it's really just in the cloud system resolving regime, but we have scaled it down to much finer resolution than 3.25, down to the sub-kilometer scale to investigate its performance, and found that in general, it's pretty scale invariant. Things look generally pretty good. Since it's part of E3SM, that also means that it's coupled to the E3SM land model, the ocean and sea ice modules. And so we can run basically the full climate system, though most of the runs that we've done to date have been primarily focused on the AMIP configuration, or the atmosphere only configuration. Just to show some kind of eye candy on overall model performance, on the left-hand side here, we see the results from the Diamond 2 simulation focused on one particular region. On the left-hand side is the Hawaii satellite visible image from January 22nd, and to its right is the corresponding image generated from the SCREAM simulation. And so just looking at these two side by side, we were pretty impressed at how well the model was actually able to duplicate the underlying meteorology that occurred there. In terms of the overall structure of the model, there's no parameterized convection. The turbulence and cloud formulation is handled by the shock parameterization. Aerosols are currently prescribed, though we're working on a prognostic aerosol module in order to plug into SCREAM. Resolve scale fluid dynamics through the home model, as I mentioned. Microphysical processes handled by P3 and RRTMG for radiation. One of the key advantages, and probably most relevant to this session, is that the home model, the spectral element formulation, effectively allows you to refine wherever you want, as long as your global grid is composed entirely of quadrilaterals. So we can do some crazy things. In the past, I've shown an image where I've only refined over top of mountains of the world. But here's something that's a little bit more applicable. This is a grid that we're using for climate studies over the contiguous US, where we wanted to capture the upstream tropical cyclogenesis region so that we could properly get extremes that would impact the eastern and Gulf coasts of the US. And we also wanted to get atmospheric river events that came in off of the Pacific, which are generally resolved at around 55 kilometer or so grid spacing. And so there we have a slightly extended refined mesh. And so we can have multiple layers of nesting at using basically these mesh refinement tools and be able to run the whole model as an entirely global simulation. This, of course, allows us to then redirect more resources for more ensemble members, greater model complexity, including active chemistry or more tracers. There are a number of tools that we've built up in the ecosystem in order to support this. So the grid generation tool is this tool known as SquadGen, where you basically give it a PNG image, which shows on a latitude longitude grid where you want that refinement, and it generates the corresponding refinement region. Here again, showing the CONUS mesh and an Arctic mesh that is used. We have a data assimilation system known as BetaCast that allows us to initialize runs with Scream in order to do either hindcasts or forecasts. And we have various tools in order to do visualization on unstructured grids, including the NCViz tool that I'm showing here, which is basically a it intends to replace the functionality of the NCView tool, except it works, again, directly on native grids, so no additional regridding is actually needed. And so we can continue to do all the operations that we would normally do on structured grids on unstructured grids in effectively a seamless manner. The beta casting framework that I mentioned is used in order to run these forecasting and hindcasting based simulations, and it allows us to basically incorporate any sort of initial data as the initial conditions for the simulation and even compose those on top of one another. And in addition, it has infrastructure set up that allows us to spin up the land model in order to be consistent with those meteorological conditions. So typically what we do is a year or more of pure land model run with forced meteorology in order to generate that land initial condition. In terms of the atmospheric data that we can specify essentially anything. And what I'm going to show you at the end here is actually where we've composed ERA5 data with HWRF data in order to produce a simulation of Super Typhoon Mawar. So why are we interested in beta casting? Well, it's not because we want to come up with a forecast model and supplant NOAA. So Lucas, you don't have to worry about that. Instead, we're primarily interested in basically understanding how the global Earth system is responding to change. And one way that we can do that is hindcast historic events and then modify those conditions in accordance with how much we anticipate climate change is affecting sea surface temperatures, atmospheric temperatures, and other meteorological variables, and then run it again in the future and say, how much does that change the underlying extreme event? So these kind of simulations are more commonly known as pseudo global warming type simulations because of this imposed additional global warming on top of the historic simulation, and allows us to get some really deep insights as to how climate change may be affecting extreme weather events. With that being said, I'm not going to mention it again during this talk because the focus of this talk is on forecasting and hindcasting. Okay, so I'm going to go through a couple examples of different events that we've simulated. So the first one I'm going to talk about is the 2012 North American Derecho. You can see the refinement region in kind of this dark boxy area there, covering much of the central and eastern US. We used rapid refresh data in order to initialize the model within that high resolution patch, just because it provided higher resolution initial conditions. And we used ERA5 to do the rest of the global domain. We then compared the simulation against analogous WRF simulations, just in order to see how well Scream actually performed as a regionally, basically a regional climate model or regional forecasting model. This event was it can be particularly challenging to forecast actually, because Derecho events are, of course, localized convective systems with high winds. And so understanding whether or not it's getting the impacts relevant meteorology correct is very important for understanding future risks from these events. So the video on the right-hand side basically shows the forecast. On the top, we see wind direction and magnitude, wind speed in particular being perhaps the most well-known impact associated with derechos, and one where the Scream model does particularly well, where we actually capture those incredibly high wind speeds that led to widespread damage from the derecho event. But looking at precipitation and upwelling long wave flux as well, it's clear that we actually got the mesoscale convective system fairly consistent with observations, essentially, as including its propagation path from basically Chicago all the way through to the eastern seaboard. This allowed us to then develop a test bed which is basically a set of evaluation metrics for particular extreme events, and demonstrate that SCREAM was consistent, if not better than WRF in most of these underlying metrics for regional simulation, which I think is a nice result because SCREAM was not really designed to be a regional climate model, not to the extent that WRF is. And so if we're doing pretty similar in terms of overall performance on this particularly challenging weather event, then I think that's very encouraging about the usage of the model for these kind of simulations. Another event that we were interested in was the 1996 Susquehanna flood. This is a rain on snow event, and so one which allowed us to exercise both the atmosphere model and the land modeling system and see if we could get the rapid melt of snow that basically led to flooding in the Susquehanna watershed. And this is an interesting case as well, because if you look at reanalysis products about this event, they actually differ pretty substantially in how much melt was produced. And so with the SCREAM model, though, we were able to get a fairly realistic looking melt curve. That is, this high precipitation event plus warm temperatures produced sufficient melt that would then be consistent with the kind of flooding that was seen in 1996 down the Susquehanna. A similar flood event was also investigated in, which is known as the 1997 New Year's flood. This is a big flood event that occurred in California back in around New Year's of 1997. Basically, a big series of atmospheric river events that came through and basically led to many regions of the Central Valley being thoroughly flooded with widespread damage and other socioeconomic damage. Interestingly, in this case, we ran the simulation down to 3.5 kilometers over the Sierra Nevada mountain range, and then used that data in order to run the WEEP model, which is basically a hydraulic model for modeling stream flow and water once it actually hit the ground. And what we actually were able to see was that with the E3SM simulation of this 1997 New Year's flood event, we were actually able to get stream flows that were much more consistent with observations and actually would hit that threshold necessary for triggering flood events. Whereas with standard gridded meteorological data, we weren't able to get the kinds of flood levels that we had seen historically. So this suggests that the model itself is actually outperforming the observations when it comes to the correct amount and intensity of precipitation. And this is something that Jessica Lundquist has actually documented before. So not a overly surprising result, but again, encouraging in the usage of models in order to perform these kind of simulations. All right, I'm told that the projector is not the greatest quality, but hopefully this video kind of shows up pretty well for you guys. This is a recent simulation that we actually conducted here to look at Super Typhoon Mawar, which hit Guam in late May of 2023, so earlier this year, and led to widespread devastation across the island and was one of the most intense storms to hit since the early 2000s. With this run, we can then look at impacts, including both extreme winds and extreme precipitation on the island, and compare those impacts results to then what was seen observationally, and again, perform this pseudo global warming type modification so we can understand how warmer sea surface temperatures and atmospheric conditions would result in intensification of a corresponding storm event into the future, so as we can better inform adaptation planning in light of this. Again, this simulation, I think, was really cool exercise of the whole tool chain because we were able to put HWRF data, that is the hurricane WRF data, superimpose that on top of ERA 5 and still run a really nice simulation that didn't crash and actually produced a fairly realistic looking super typhoon. All right, just in order to wrap things up then, in terms of DOE interests in nested grids and using the SCREAM model, we're interested in building more large ensembles so that we can get a better sampling of future extremes or extremes that could have happened historically but did not because we were lucky, so that we can get, again, a better idea of what kind of weather may be thrown at us in the future and how we can be prepared for those type of impacts. We're interested in more storyline simulations to understand how historic weather events may manifest again if they occur within the future. And we're interested in linking this with impacts models, particularly electrical infrastructure and flood models, in order to understand how risks from climate impacts may be changing into the future. So with that, I will wrap up and say thank you very much for the invite, and I hope you enjoyed the talk.
Thank you, Paul. We save the question to the end, the Q&A session. I hope you can stay and answer some questions 5 o'clock Mountain Time. Is it 5? Yeah, 5 o'clock Mountain Time. So next talk will be Pinzu, Professor Pinzu from FIU. Pinzu, are you there?
Yes.
Yeah.
Can I share?
Yeah.
Can you share? Can you see it?
We can see your screen.
Okay. Can you see the full screen?
Yes.
Okay. Thank you, Jane. Good afternoon. First, I'd like to acknowledge my NOAA collaborators for this work, Dr. Jun Zhang, Dr. Xujin Zhang from HRD, Dr. Jiren Bao from PSL, and Dr. Zhang Zhang from EMC. First, let me make a brief review of how turbulence is parameterized in current mesoscale and large-scale models so that we can get a better understand why a three-dimensional representation of turbulence is needed for numerical models. In favorable conditions, the turbulent boundary layer is cleanly separated from the free atmosphere by a cupping inversion, as illustrated here by the typical continental convective boundary layer, subtropical trivial marine boundary layer, stratocumulus toppled marine boundary layer, and a stable nocturnal boundary layer. In addition to the common vertical thermodynamic structure, in all these cases, the vertical turbulent mixing is much stronger than the horizontal turbulent mixing. So in mesoscale and large-scale models, horizontal and vertical turbulent mixing is treated separately, with the former being handled in the model's dynamic solver using a relatively simple approach. For example, the Smagrinsk scheme, which simply relates the fluxes to the shear string of the mean flow. The vertical turbulent mixing, on the other hand, is treated in a standalone module outside the model dynamics, which can be very sophisticated depending on the order of closure, local or non-local mixing, and dry or moist thermodynamics to exclude or include the cloud effects. Like many other physics parameterization, the PBL scheme is constructed in a one-dimensional vertical column fashion so that the different 1D schemes can be bundled together in what is called a model physics package. But the separation of model physics from model dynamics does not always work well. For example, in the inner core of the tropical cyclones. The left panel here shows the vertical thermodynamic structure in the eye wall from the drop zones collected in Hurricane Earl and those from Hurricane Patricia and Ida simulated by H-Wolf and Halves, respectively. Despite different hurricanes developed under the different conditions, the theta profile in the eye wall is very consistent in the entire troposphere, in which no inversion exists to separate the boundary layer from the free atmosphere above. This is in stark contrast to the CBL, MBL, and SBL that I showed previously. The two figures on the right shows the LiDAR retrieved the turbulent kinetic energy in Rita and the composite TKE retrieved from many hurricanes. Large TKEs are seen in the eye wall throughout the troposphere. There is no interface to separate the turbulence generated by the boundary layer processes and the cloud processes aloft. So the traditional PBL concept does not apply here because it does not faithfully reflect the turbulent structure in the eye wall. In addition to the unique turbulent transport in the eye wall, how to appropriately represent horizontal turbulent mixing in the inner core of TC is also an issue. The left figure shows a snapshot of a cross-section at the outer edge of eye wall from a large AD simulation of Hurricane Isabel, as indicated by the black arrow. Large turbulent ADs not only experience large lateral contrast across the eye wall to generate compatible and interconnected horizontal and vertical mixing, but also entrain molten air laterally into the eye wall. Using the in-situ aircraft measurements, we examined if molten air laterally entrained into the eye wall meets the instability criteria. The results show most of data points fall clearly in the unstable regime. The lateral entrainment instability promotes TKE generation in the eye wall, which in turn causes more theta E molten air to be entrained into the eye wall. This unique positive feedback and the comparable interconnected horizontal and vertical turbulent mixing poses a challenge for the separated vertical and horizontal turbulence parameterization. The problem becomes even more serious when molecular resolution increases to the gray zone. As we know, large eddies are generated by the instability of the mean flow, and therefore they're fundamentally anisotropic. Eddies smaller than inertial subrange are considered to be isotropic. When molecular resolution increases to the inertial subrange, the unresolved small-scale turbulence needs to be treated three-dimensionally under the isotropic assumption. This is known as the large eddy simulations. In mesoscale simulations, the directional dependent turbulent mixing induced by unresolved large anisotropic turbulence is currently handled by the separated vertical and horizontal turbulent schemes. When molecular resolution is low, this approach works fine because the vertical turbulent mixing is much stronger than horizontal turbulent mixing. But what about the turbulent mixing when molecular resolution increases to the gray zone? Like the eddies at the eye wall that I just showed induce comparable interconnected horizontal and vertical turbulent mixing. In this case, the purely 1D column framework for parameterizing vertical turbulent mixing and the separated horizontal and vertical turbulent mixing becomes a problem. So when model grid resolution increases to the gray zone, the physics dynamics coupling becomes increasingly important. The separation between physics and model dynamics becomes an obstacle to model development. To relax the problem funded by JTTI program, we are currently developing a scale-aware 3D TKE turbulent scheme to bridge the gap between LES and MS limit. The TKE budget equation may be written like this using Einstein notation. In 3D framework, the shear production tensor contains 9 terms. The TKE transport and pressure correlation has 3 terms in XYZ direction. But in 1D framework, the shear production reduces to 2 terms, and the TKE transport and the pressure correlation becomes 1 term. But the omitted terms are not always unimportant. I'll show shortly that the full shear production tensor and the 3D TKE transport and the pressure correlation are important to turbulent transport in TC in the core, and including the omitted terms improves halves a skill in predicting TC intensity. In TKE turbulent schemes, the total turbulent fluxes may be decomposed into local and a non-local component, where the local component is calculated using down-gradient diffusion approach closed by the eddy exchange coefficient, which is a function of the predicted TKE. At the LES limit, the non-local fluxes becomes 0 and the directional dependent eddy exchange coefficient becomes isotropic eddy exchange coefficient. At the MS limit, the directional dependent eddy exchange coefficient becomes vertical and horizontal eddy exchange coefficient used in mesoscale models. And of course, in this case, we need to consider the non-local transport induced by unresolved large turbulent eddies. So here we use a blending method proposed by Zhang et al. 2018 to transition a 3D TKE scheme from LES limit to MS limit by defining a partition function for local fluxes, where delta is a model grid spacing and ZI is a diagonal's boundary height. Here we assume the scale of dominant energy containing eddies is equivalent to this height. A PL becomes 0 and 1 at the LES and MS limit. Then we can use a PL to blend the eddy exchange coefficient for a model in the gray zone like this. Similar blending method can be used to determine the non-local fluxes for a model in a gray zone like this, and the non-local fluxes at the MS limit are determined by the mass flux approach. For implementation of the scale-aware 3D TKE scheme in halves, we place the main body of the scheme in CCPP, but the TKE shear production tensor and the 3D TKE transport and pressure correlation are calculated in the dynamic solver and then transfer them to the CCPP. Using the halves with the new scheme that we just implemented, we simulated the Hurricane Ida. This figure shows the simulated storm track and intensity compared with observations. Here, the black line is the best track. The gray line is the baseline half simulations using the default model physics. The blue line is the simulation that uses a new scheme but only considers 3D TKE shear production tensor. The green line is a simulation that considers both 3D TKE shear production tensor and the horizontal mixing parameterized using the predicted TKE. The red line is a simulation that considers 3D TKE shear production tensor, TKE-based horizontal mixing, and 3D TKE transport and pressure correlation. As you can see, the scale-aware 3D TKE scheme substantially improves half scale in predicting Ida's rapid intensification and peak intensity. So in summary, the purely one-dimensional vertical column framework for parameterizing vertical turbulent mixing and the separated horizontal and vertical parameterization poses an obstacle for realistic representation of three-dimensional turbulent transport in the TC inner core. A scale-aware 3D TKE scheme showed a promising result to improve half the scale in predicting TC intensity, at least for its Ida case. And for future work, we will conduct sensitivity tests to evaluate the scale-aware 3D TKE scheme for various resolution settings and further refine and tune the scheme. We will validate the half simulations of historical hurricane cases with different intensities, major hurricanes and weak tropical storms against observations. We are also planning to perform real-time TC forecasts maybe in 2025 Atlantic hurricane season. And this is all I have. Thank you for your attention.
Thank you so much. We saved the question to the Q&A session, and if Ping, can you stay to the Q&A session?
Yes, I'll stay.
It's a little bit late in Eastern.
No, that's fine. That's fine. Thank you.
I want to like all the speaker can stay then answer questions, and we have questions in the room and online. Thank you so much. And then the next speaker will be Jim Purser. Jim coming from EMC, he still will present from virtually. He will present from EMC.
Okay.
Sure.
Let's
Great, Jim.
you see this?
Yep.
You see everything? All right. Yeah, it's all right up here. I think it's.
Mic is on. Is mic on?
And you can hear me, right?
Yeah, we can hear you.
All right, I'll start.
You're live.
This is the team that we've all contributed to this project, and I was actually brought in relatively late, I suppose, by Tom Black and Gerard Katefian, who said that they're having difficulty getting a reasonably uniform resolution grid to cover a large area. So that this talk will describe the process by which we have extended this Schmidt mnemonic concept for producing grids, specifically for limited area applications. I'm trying to advance. Whoops. The motivation for this work is that the cube sphere model came from Lucas and his colleagues with variants of the mnemonic projection grids spanning each of the 6 faces of the cube. So in each case, the grid lines were great circles defining families of planes intersecting along the axes through the center of the Earth. And we shall consider that the Earth to be a unit radius sphere from now on. And each of the variants of these grids were distinguished by the way that the grid lines were separated as you go out from the median of each cube face. In addition, the FV3 cube came with the globally smooth, the classic Schmidt focus refinement option, which is a conformal or angle preserving mapping of the sphere to itself. Now, the problem is that for large limited domains, no paired combinations of these two mapping options was found to be able to provide the sufficiently homogeneous, undistorted grid that we needed for numerical weather analysis and prediction. Therefore, we sought a method to expand the existing space of mapping parameters that could then satisfy our limited area needs. If we look at the variations that you can put on the mnemonic grid line spacing, you can actually consider the provided grids that came with the cube to belong to a continuous family with what I call a parameter B, and the angular distance, at an angular distance away from the median of the face, you can draw an arc. Arc costs square root of B from the face, so that angle, and along which the transverse grid lines were uniform. Now, in the old days when Sadorni, back in 1972, he first proposed this cubic grid, he used what we call the equidistant spacing, which means that the grid lines as projected onto the tangent plane would be equally spaced. And in 1996, in a Journal of Computational Physics paper, Ronchi et al. Proposed the equiangular spacing. So the former grid would correspond to B equals 0, and the equiangular spacing grid would correspond to B equals 1. But we can use anything in between. The mnemonic grid arcs form great circles when successive planes of these great circles are uniformly spaced in angle at the common axis. We call that the equiangular mnemonic. And the B parameter could be extended beyond its range of 0 to 1, corresponding to trigonometric algebraic formulations, by a process which you can think of as being an analytic continuation. If you do extend the B parameter to larger values than 1, you have to start using the hyperbolic cosine instead of the cosine, for example. But it's a perfectly valid algebraic extension of that particular parameter. And you can also extend it to some degree to B being less than 0. And the figures I show at the bottom of the slide show these examples of these limits being exceeded. They're not particularly useful grids, but it does show that you can expand the parameter space of the mapping. And incidentally, the version of the FV3 cube that we use operationally, it corresponds to the case where the transverse grid lines are uniform along the edges of the cube. And that corresponds in this notation to the B equals 1/2 option. So let's just talk about the next part of the transformation, the Schmidt refinement. The FV3 cubed grid was equipped with a second parameter, the Schmidt conformal refinement factor S, and it works, you can think of it as follows. The mnemonic grid is formed by families of straight lines on the tangent plane to the sphere, which is shown blue here. I hope you can see the colors. And centrally, you back project this, at least conceptually, to the unit sphere, to the point big X, and then propagate or project stereographically from the antipodal point, the South Pole in this case, onto the equatorial plane. And then you have your stereographic mapping. So that's the first step. Now what you do is you can shrink the image on that equatorial plane, and you can project back onto the sphere, and you will have an enhanced resolution at the focus or the projection point of interest, in this case, the North Pole, if the shrinkage that you affected was a 1 over S factor. So let's look at how this can be generalized. So the idea is, what if we replace the parameter S by K equals S squared? And then in this equivalent picture, we can think of K as being the Gaussian curvature of a sphere, which is not of unit radius, which we to start with. So we have a sphere of radius 1 over S to begin with, and we do the same construction of the mnemonic grid on that from that sphere. But now we use the shared equatorial plane, and the final step is to back project it onto the unit sphere, unit radius Earth. So that's an equivalent way of thinking about what the Schmidt transformation does. But the wonderful advantage of having a parameter that we call the Gaussian curvature, the K parameter, is that it is not necessarily going to always be positive. We can allow it to become negative. So instead of having a real value for the radius of the sphere, what we are effectively doing is taking an imaginary value. Or we can just think of the second way of describing the Schmidt transformation as starting with a mnemonic grid on the, let me just show, I think I'm a slide behind, a mnemonic grid on the hyperbolic plane, which is described using hyperbolic geometry shown here in the right portion of the slide. So again, we start with the straight line grid on the tangent plane, the blue here, back projected onto the hypersphere, which is up here, and we perform the stereographic projection onto the equatorial plane, which is the red central plane here. But now we transfer over to the spherical case, and now we take that image, we just transport it over to the equatorial plane of the real sphere and project it back onto the Earth, and then we have our extended Schmidt mnemonic grid defined. So what's the advantage of doing this? Well, the conformal mapping of the sphere to itself to enhance resolution of the sphere, which was proposed by Schmidt in 1977, was originally defined to be a transformation of the whole of the sphere to itself. And these transformations are known by mathematicians who work in the complex plane, when it's a mapping from the complex plane to itself, as Möbius transformations, and they form a 6-parameter continuous group. And they're quite important in applied mathematics. By replacing the parameter S by the parameter K, which is just S squared, we can extend the range of the Schmidt mappings, but they will no longer apply to the whole sphere because we get a singularity in the mapping away from the region of interest. But of course, it's perfectly okay to use this kind of mapping for a regional model, and that's just what we do. So there is one other thing that we need to do after this in order to regularize the mapping parameters as we go from the K greater than 0 to the K less than 0 case. It is helpful to regularize the other parameter, the B parameter, by multiplying it by the K, and we call that parameter A. So if you ever use the ESG, the extended Schmidt mnemonic system, you will come across the 2 mapping parameters A and K, which are optimized. Now the question is, how do we optimize this mapping? Well, what we're trying to do is to get a mapping onto a finite region, a rectangular region on the sphere, which is optimized with respect to the amount of distortion. So we quantify the distortion by looking at the Jacobian matrix, the rate of change of the Earth-centered Cartesians with respect to the map coordinates, the X and the Y, or the X1 and the X2.
We got about 5 minutes left.
Okay, we generate from that the Gram matrix by taking this rectangular matrix J, the Jacobian, the JT times J gives you the Gram matrix, which is a 2 by 2 matrix at every point. And the objective should be to minimize some kind of variance of the G, since this can serve as an objective measure of the map's overall inhomogeneity. And we do this to quantify the inhomogeneity. We want to get some kind of scalar quantity out of this. And the way that we can do this is to first define the logarithm of the matrix, which is defined in this equation here, and get diagnostics based on that. So if you recall, if you rescale the map coordinates, it only has an additive effect on L. So we can redefine L by subtracting this mean constant part of it and define a parameterized diagnostic Q, the quality of the map, which quantifies the inhomogeneity. And we do that using a parameter gamma that enhances or emphasizes the amount by which the areal inhomogeneity of the map shows up. So the first term here is really the I suppose it's a Frobenius norm of the logarithm of the Gram matrix. And the second term here comes from the trace itself squared. And what we want to do is to minimize Q, because this represents the distortion of the map. So I've shown the equation again. Oh, by the A in the denominator is not the A parameter that we had before in the mapping. Sorry about that confusion of the notation. But if you do that, if you do this integration over the rectangular region and minimize it, then you get what you can call the best mapping for that domain with respect to that lambda parameter, that
Jim, 2 minutes left.
The gamma parameter, sorry. The gamma parameter will be, when it's large, you're emphasizing the areal inhomogeneity, and when it's small, you're ignoring that and just looking at the distortion. And to show that this works, we use a gamma parameter of about 0.8 typically. And this slide shows the tremendous reduction of the inhomogeneity of the mapping that you can get, as shown on in the left side of the picture, when you use the ESG grid compared with the ordinary mnemonic grid. And so the final remarks, the ESG grid allows rectangular domains of very large geographical widths to be represented with very little distortion. They produce some flaring of the grid at the edges and a pinching of the grid at the corners. And the A parameter can be of either sign for large rectangles, but the K parameter tends to be negative. So we really do use this extension of the mapping. And my final conclusions is just to say that well, reiterating what I've really said, so you can read that. And there I finish. Thank you.
Thank you, Jim. And we save the question to the Q&A session. And Jim, you stay. If anyone asks you a question, you stay.
Sure.
Thank you. Next speaker from GFDL, Joseph Millen. I don't know how to pronounce his last name. Mullen. Okay. Yeah, Joseph, go ahead.
Can you see my slides and can you hear me well?
Yes.
Okay, hello everyone. Thanks for attending my talk. So today I will be talking about novel grid capabilities that we have implemented in FE3 in the last 3 years. And given that Lucas has already presented FE3, I will just dive in and talk about in particular these two projects, the multiple grid nesting, where we implemented multiple same level and telescoping nesting in FE3. And this project has already been completed, and it's on the public repository of FE3 on GitHub. And on the right, the GeoGrid, which is a new project that is currently under development. So first, let's start and talk about nesting in FE3. So it is still impractical so FE3 employs a cubed sphere grid, as you all know, and it's still impractical to run a very high resolution global models with a resolution high enough to capture small features in flow that are necessary to capture special weather events such as severe storms and hurricanes. And even if we are able to do that, we generate a lot of data that we sometimes don't talk about, how to post-process the data and how we can handle this amount of data. So what we have in FE3, we have two strategies or two variable resolution strategies. We have the grid stretching and grid nesting. So grid nesting consists of adding one additional tile or grid in one of the cubed sphere tiles here over an area of interest. So here on the right, we have two examples that we use in Shield, which we develop here at the FE3 team. We have this C Shield configuration where we have a nest over Cornus with a resolution of 2.5 kilometer for severe weather prediction, starting from a 13 kilometer global resolution. And here we have a nest over the Atlantic in another configuration called T Shield for tropical cyclones. So we took this technology and we extended it to support multiple same level and telescopic nesting, as I will show you a little bit later. So in FE3, we have different levels of time stepping. We have a long time step called DT Atmos. We have a middle time step or a mapping time step and a fast time step, the acoustic time step. So how nesting works in FE3, basically on the top right, you have a parent grid where the nest is located, and here you have the nest. So basically what we do is every remapping time step or this time step in the middle, we update the boundary conditions of the nest, which is region 4 here from the compute domain of the parent grid or region 1. So we do that by doing linear interpolation of all variables from 1 to 4. Then we do a linear extrapolation of these variables here in region 4 for every acoustic time step. So they are not fixed every acoustic time step. And then we let each grid run differently on different sets of processor. Each grid can has its own name list and can be configured differently. And then every long time step or DT Atmos, we do a two-way update where we average the data here from the nested grid domain 3, and we replace it here in the compute domain where the nest lies. So what we do at the moment in nesting in FE3, we only update the temperature and the 3 wind components. So basically, we are not really violating any conservation properties on the top level parity grid. So here a little bit about two-way nesting. So for a cell mean scalar or a cell center scalar, such as temperature, we do an area weighted average of these small squares here to get the average for the big square, and for the winds, the G-grid winds, we do a length weighted average of the yellow small arrows to get the big arrow here. So this is just a schematic to make things very simple. Basically, the grids are not square, or they are non-orthogonal quadrilateral. So here are some results of the multiple nesting framework. So what you see here in the middle is animation of the vorticity at the top level at 850 MB of a global resolution of Hurricane Laura with a 200 kilometer global resolution for the 6 faces of the cubed sphere. And we have here implemented 4 nests. For instance, we can have 3 nests at the same level with a resolution of 50 kilometer and a telescoping nest here of 12 kilometer that you can see here with a resolution of 12 kilometer. And then what you see here is actually the vorticity only on the top level field. So what we do is like you can see the effects of the two-way update up to that 200-kilometer resolution, and you can see these small details captured where the nests are located. And you can see that we can capture how the hurricane is landing here, some severe activity in the west coast of Mexico, and here the initial formation of Typhoon Maisak, which apparently happened at the same time of the landfall of Hurricane Laura. All of them starting from a 200-kilometer resolution grid. So the nesting framework is very flexible. We can use the nests in different layouts. Here on the right, we have, for instance, different level of telescopic nesting, and you can see here the precipitation and the integrated water column here on each of the resolution, 13, 4, and 1 kilometer. And here on the right, we have an example of a test case in a parent regional domain of an atmospheric river in California with a parent resolution of 50 kilometers, 17 and 6, with 2 nests embedded in this regional configuration. So you can see all these results in this paper that we published in GMD, and we have transferred this technology to HAFS, which became operational a few weeks ago. So congratulations for the HAFS team on that accomplishment. So let's move on and talk about the second project, the GeoGrid project. So while the cubed sphere has a lot of advantages from having quasi-uniform grid areas, very easily parallelizable on HPC systems, we don't have the singularities on the poles. It has an issue with the edges and corners. So basically, if we are on one face of the cubed sphere here, we have a discontinuity here at the edge, and then we are basically integrating like not in we have this discontinuity here. So basically a grid discontinuity will manifest as a discontinuity in the numerical solution. So, and then you will see the structure of the grid in the numerical solution, which is not desirable. So we already have an edge handling code that try to minimize this discontinuity, but it still exists. So what we did here is we employed a new system, or we implemented it in FE3 called the GeoGrid, where the GeoGrid is a system comprised of 2 grids, the king grid and an extended grid. So basically we take the data from neighboring processors on a king grid, and we remap them along the extension of great circle lines coming out from the compute domain of here that you see the blue domain here. So we can simply just integrate without having any discontinuity in the grid, and that way we eliminate the discontinuity in the numerical solution. So we have implemented that in the message passing calls in FE3, so other developers don't have to deal with all this code. And a huge advantage for that is basically the future development of FE3 on GPUs. So basically, if we don't have all the edge handling code, we can simply just perform the same numerical operation on the data here in blue and the red region. We don't have a separation here, so we just can dump all that data on GPU, which is very desirable for a future CPU GPU hybrid system. That way we can minimize the movement between the CPU and GPU. And my colleague Oliver Albert is doing a really good work on porting FE3 onto CPU and GPU hybrid systems. So there has been many challenges to implement this code in FE3. So basically we took the original GeoGrid from LMARS, from my colleague Chi Chen, where he implemented that on unstaggered cell-centered grids. And we extended that code to support different grid staggering, the corners, the B grid, the C winds, and the D grid winds. It was not very straightforward for staggered winds because, as you can see, the component of the winds lie on different places, and if you are on the edge, you have one component on this face, the other component on the other face. So it was a little bit challenging to find a good and fast and efficient solution to do that. Here on the corners, we implemented this edge or the corner handling algorithm to populate the corner region with correct data, and it wasn't also take down optimized subroutines in FE3 in order to implement all this. So we have performed many shallow water tests, and we have now a paper under review. So we have here the different advection tests from the Williamson test cases, the cosine bell advection test, the geostrophic case, the Rossby wave, and here the colliding modon case, where we have two pair of vortices that move one to the east, one to the west. They meet here in the middle. They exchange vortices. They travel to the other side. They meet again. They exchange vortices, and they come back to their initial solution. So that was a really nice test to pass, which makes the implementation very robust and will show any impurities in the implementation of any code in any dynamical core. Here are the results for the case 2, the geostrophic balance flow. So here on the left, you see the zonal wind, the intensity of the zonal winds. And here in this column, you see the evolution on the kinked grid on 1, 3, and 5 days. So here I'm showing on the first day the layout of the grids, and then here on starting from the 3rd and 5th day, we removed the grid layout, so you can see here the meridional wind field, and ideally this should be 0. So what you see here, the numerical solution on the kinked grid, you can see that we can see the structure of the edge at corner, and then all this noise will actually propagate inside the domain and contaminate the numerical solution. And on the right, you can see that we have been able to greatly reduce this noise for this test case. So this is on 200 kilometers. For the Rossby wave, usually this wave is also a stress case for dynamical cores. So a threshold in the literature is 14 days for most dynamical cores. Basically, it will test the ability of a dynamical core to hold the Rossby wave as long as possible, and then it will break due to many reasons, truncation errors, grid staggering, and many other different reasons. In FE3, we are able to maintain the shape of the Rossby wave for around 80 to 85 days when it starts to lose symmetry, and then it breaks. So that's the original version of FE3. Okay. And on the right, you can see the results of the Rossby wave employing the geogrid, and we can maintain the wave for more than 100 days. So this is a very good result and robust result. Last but not least, we extended the implementation for the non-hydrostatic 3D solver, and what you see here is the baroclinic wave with an instability in the north hemisphere. And this is the meridional winds, and everything you see here in the southern hemisphere is due to grid imprinting. So on the left, you have the kinked grid. On the right, you can see the solution, the evolution of the solution on the geogrid, and this is also for 200 kilometers. So all these results are now under review, and we are expecting to get this paper to be published very soon, maybe next month. So if you have any questions, please feel free to reach out to me and Lucas, and I'm happy to take any questions in the Q&A session. Thank you.
Thank you, Joseph. And we save question to the Q&A session. Stay there, then we ask questions. Next speaker, Bill Armstrong from LML. He will talk about moving nest.
Good afternoon. I'm going to be speaking today about the moving nest features for HAFs. I've worked on this the last several years with my collaborators at AOML and EMC, and with a lot of good discussions from Lucas and Joseph at GFDL. How does this thing work? So the overview of the moving nest, as Joseph mentioned, we have limits in the global forecasting system. Currently, we're running the global GFS at 13-kilometer resolution. course, to model hurricanes accurately, we're looking at, we'd like something on the order of 1 to 4 kilometer resolution to capture the strong gradients in the eye wall, rain bands, these sort of features. And these are not currently feasible to run at the global domain, particularly in operational timeframes. So we've implemented the high resolution nesting. And the idea of this is to have storm following nest to give us a high resolution for the tropical cyclones. This development has several different ways that it can be configured, from a regional configuration to a basin scale, as well as global configurations. And the operational configuration will be the storm-centric regional. So this implementation has just gone into operations as of June 27th for NOAA. We have 2 different configurations that are in operations with different sets of physics options. Both of them have a similar grid definition, which is a 6-kilometer regional parent and a 2-kilometer moving nest. Example shown on the right for Hurricane Ida. This is about 4 years of development work has gone into accomplishing this. Some of the features of the moving nest, we saw some longer presentations about all the details of the performance from Zach earlier today, but a summary is we're seeing track improvements of about 5 to 10% more accurate than HWRF. Similar improvements for wind speed. This also code is quite fast. The runtime overhead is 3 to 7% compared to a static nest of the same size. And as you might expect, that scales with the forward motion of the storm. So if you do more nest moves, that's towards the 7% for fast moving storms. In comparison, the HWRF overhead is on the order of 15 to 20%. So this we were able to get a lot of efficiency with this implementation. We did a lot of retrospective testing with the group at AOML and EMC to examine the cases from 2020 through 2022, to look at basically all the cases in the North Atlantic and East Pacific, and a number of cases in global basins, including stress tests of Southern Hemisphere, crossing the date line, et cetera. And this is quite configurable with the name list options. In terms of how this is implemented, one of the main features that we were able to leverage was the existing Halo code that Joseph referenced a little bit, which is used for downscaling and transmitting data from the coarse resolution to the fine. So that's normally used just for the boundary conditions of the nest, but we also use that to supply the data needed when we decide to move the nest. The prognostic variables there must be moved, and then a variety of other variables that I'll get to. This nesting is currently implemented where the nest points are aligned with the parent points. This makes for enhanced efficiency as well as enhanced precision in terms of the feedback, so that we have just simple addition when we feed back to the parent, for instance. So in terms of the model variables that are handled, the first set that we handle are the main prognostic variables for the model: the temperature, the height of the layer in del Z and del P coordinates, the UVW winds, humidity, moisture tracers, et cetera. Those are in 3-dimensional arrays, basically, so they're handled in a relatively straightforward way. Now, the physics variables instead, in the implementation in the model, there's about 56 variables that we handle, and those are mostly handled as 1D arrays for efficiency inside the model core. So we first transform those into 2D arrays so that we have the topology to know how to shift them accurately when we move the nest, perform that nest, and then retransform them back to 1D arrays. Another set of data that's dealt with are the static surface fields, things like land sea mask, vegetation types, these sorts of fields. We generate those at the nest resolution, the high resolution for the entire parent grid, and have those as files during the pre-processing steps. And then those are read in when the nest moves. Finally, the grid distances, areas, Coriolis, some of these sort of navigation parameters, those are calculated at 64-bit precision. It's a little cut off there on the slide. Apologize for that. One of the other features of the moving nest is the internal tracker. So this tracker was ported from the HWRF code and is based on the GFDL tracker that Tim Marchok and others have worked on, where we evaluate the center using 9 different variables at several different levels. So at the surface and near surface, we look at sea level pressure, 10-meter winds, vorticity. Then at 850 and 700 millibars, we look at the winds, the vorticity, and geopotential to come up with a variety of estimates of where the center is. Then we combine those together so that the tracking is more robust to passing over land or terrain, or also, you know, cases where perhaps there's not a strong signal at the surface for some weaker systems. So some of the current work that I've been doing this year since spring is implementing multiple moving nests. So this is leveraging that work that Joseph did of static multiple nests. So been implementing these multiple nests to run again in the regional, basin, or global configurations. These will also have the parallelism the same way that the the multiple static or the single moving nest is, such that the parent runs on one set of processors, each nest will run on another set of processors, and be time stepping concurrently due to the design of FV3. So that's a very efficient thing for the model. One of the steps that we'll be considering coming up in the next few months is looking at cases where those nests may overlap, is, storms approach one another, of how to potentially merge that feedback. So here's some results of the current state of this coding for the multiple moving nests. I now have some dual nest cases running. I have some coarse resolution cases that I've been using for the development and checking out the mechanics of the nest motion. And then I have some cases such as this one of Sally and Teddy that are at high resolution. So this is a 6-kilometer regional parent with 2-kilometer nests. It's basically the half speed configuration, except I shrunk the size of the nests a little bit just to make sure they wouldn't overlap on each other for this particular case. So I'm still doing validation to make sure that everything is running, accurately on these. And then the upcoming tests will be looking at running 3 or more concurrent nests, which will be the next step. And then starting to get into seeing how it behaves when the nests overlap as storms approach one another. And also, this should be able to support running a mix of some nests moving and some static. So you could, for instance, put a static nest over Florida or somewhere and then have some moving nests following storms. So part of the motivation for going towards the multiple moving nests is we've been talking about implementing a half basin scale. So this would follow on to the work that Gus and others at AOML did for the basin scale HWRF. So it'll be a diagram similar to on the right there. The idea will be to have multiple nested domains covering the NHC area of responsibility, so getting the whole North Atlantic and East Pacific. One of the other benefits, along with capturing the storm-storm interaction, is that this will be better suited also for data assimilation by having a static parent nest rather than the current configuration where the parent also moves depending on storm centers. So then we'll be able to more easily cycle data assimilation over multiple days. So this is a development that's going on right now with the moving nest, as well as a bunch of workflow changes to permit this development. And then in the longer term, we have this storm-centered version running for 2023 in the 2 configurations that have been discussed today. Longer term, we're looking at implementing the basin scale with multi-storms. Also going to various refinement ratios, so some higher refinement ratios. Right now, the nesting is at 3x resolution, basically because it's tied to the HALO code from FMS. And then the long term, this diagram that we've seen already this week, that is the long term of the fully global configuration with nests that can cross over cube edges and perhaps cube corners. So we won't do the questions right now, but also I'd like to just put a plug again for the AOML model viewer. That's at storm.aoml.noaa.gov to look at the halves A and halves B, the current operational halves, as well as the real-time parallels that are going on this summer. Thank you.
Thank you, Bill. Keep the time. We have a few minutes break, then we come back to the Q&A session. Is that the arrangement, the break time? Or we continue? Okay, so thank you, everyone. And come back 15 minutes and we have a fun session. Huh? Oh, it's combined or still separate? Why? Only 30 minutes?